right, so welcome to the 10th annual Cherry Point Aquatic Reserve Science Forum. This was started 10 years ago because there was a proposed coal export terminal at Cherry Point, and folks wanted to raise awareness about the Aquatic Reserve and all of the really great, awesome work that's going on out there research-wise, so that we can better learn how we can manage and protect it. So, all right, I wanted to start off with a land acknowledgement. We are deeply grateful for the enduring care that the local tribes have taken care of this area, specifically at Cherry Point. The Lummi Nation and Semiahmoo have traditionally lived at the Cherry Point area, and I included this opalescent nudibranch just as a reminder of the beauty of the area and the enduring care that those folks have put into this area. And there are many other tribes that also share usual and accustomed grounds at Cherry Point as well, that we also, I encourage you to learn more about, and feel free to reach out if you want more resources on that. So a little bit about Zoom webinar. I'm sure everyone's more or less familiar with Zoom, although I find Zoom keeps us all on our toes. There's always new things out there, but we are in Zoom webinar format today. Thank you so much for joining us too. I'm kind of glad that it's not so sunny this this morning. It's a little bit overcast. It's more your stereotypical Pacific Northwest fall day. And so it's a great morning to be on Zoom. And so you all will be muted with your video turned off. Please type questions into the question and answer box, or you can also type it into the chat box. We'll try to manage both, but if you can keep it into the Q&A box, it's a little easier for us to manage. And you can ask questions at any time, but we will be waiting until the end of each presentation to really go through those questions and answers. This is being recorded, like I mentioned earlier, and you will also get a follow-up email with links relevant to today, as well as the recording. And if there's anything at the end that we weren't able to get to that seemed really important, we'll try to follow up with that as well. So this used to be held in person, and we switched to Zoom, which has its pros and cons. You can be joining today in your pajamas, eating your pancakes, whereas we couldn't really necessarily, I mean, I guess you could do that in person, but so we're doing this again by Zoom this year. We'll see about next year, but we appreciate all of you tuning in today. Here's a quick glance at today's schedule. Robert Kaye from the Cherry Point Aquatic Reserve Citizen Stewardship Committee will be speaking a little bit about their work and why they're hosting this event today. And then after that, Iselle, Flores, Ruiz will be speaking on microplastics. Raisha Lovindeer will be talking, Raisha Lovindeer will be talking about oil spills and impacts to the marine ecosystems. We'll have a short break, and then Jessi Florendo will be speaking about kelp, and we'll be wrapping it up with Lillian Aoki about eelgrass. So it's a really wonderful lineup that I'm really thankful for all of them being here today to speak about their specific areas of research. And so should be great. A little bit about who's hosting today. I am Eleanor Hines, the North Sound Beekeeper Lead Scientist at Resources. We are part of the International Waterkeeper Alliance for Fishable, Drinkable, Swimmable Water at Resources, which is a Bellingham-based nonprofit organization that supports the aquatic reserves. So Washington Department of Natural Resources has 8 aquatic reserves throughout Washington state, and 2 of them are here locally at Fidalgo Bay and Cherry Point. And so we help support both of those aquatic reserves through their citizen stewardship committees. And we also have AmeriCorps who help support those committees, including Hannah Pittman, who just started her AmeriCorps, I think 2 weeks ago, so she is brand new, and Rondi Nordal, who put together the lineup of speakers today and put a lot of really great work into this presentation that you're going to see. So without further ado, I'll pass it off to Robert to talk a little bit more.
Okay, hi everybody, and thanks so much for coming out. Thanks, Eleanor. I'm always jealous whenever I see her title because I just think being the bay keeper has got to be the coolest job title of all time. She's wonderful. Anyway, I was asked to just say a little bit about what CPAR is and particularly about what the committee does. Eleanor kind of covered a few of the things, but what is CPAR is just go to their website and they'll give you some bullet points. It's one of 8 aquatic reserves in the Western Washington area. It has unique aquatic ecosystems, and this one is along the Straits of Georgia, the Cherry Point one is. If you don't know, most of you may already know, it basically runs through the shore from Birch Bay State Park around Point Whitehorn to the Cherry Point refinery lands. And as Eleanor said, it was first established in 2010. And it's a special place for forage fish habitat, birds, marine mammals, and it's just an all-around pretty cool place. The committee, the Citizen Stewardship, used to be the Citizen Stewardship Advisory Committee. Somewhere along the line that got dropped, but that's probably a good idea because it was already the biggest mouthful ever anyway. So that's a good thing. The website says it's a citizens committee that organizes volunteer surveys of intertidal species, works with public education, and pays attention to nearshore ecology and land use planning issues that impact the reserve. So you can just go to the website and see that, and that's kind of the bullet points. But I just want to say a little bit about what my experience has been in almost 7 years on the committee. And I'm not the oldest one by any means. There are several people that have been participating in this committee far longer than me, but they asked me to talk, so I said yes. For me, it's what happened was, along with my spouse, Deborah, we moved to this area, Birch Bay in particular, about 7 years ago to live here full time. And we really were looking for things that interested us about our local area. And we met a person who is now our good friend, Lyle Anderson, who was already on the committee. And, long story short is he said we should come check it out back in the days when we had in-person meetings at Resources, which were fun. And I really had no idea what it was going to be about, but we just thought, well, we live here now and we should find out more about it. Well, we were quite pleased and surprised what we found. We found a wonderful group of people and with truly amazing scientific knowledge. I am not a scientist by training. A lot of these studies and things have been a great learning experience for me, and I've really appreciated it. But the people who've been on the committee are longtime scientists or community scientists if they're not formally trained, and it's very impressive. We made friends. We've really had a great experience without a burdensome amount of time commitment to do it. You kind of put into it what you get out of it. So, most important, the committee offers something that is pretty hard to get otherwise, and it offers an opportunity to be a watcher for what is going on with the fossil fuel corporations that operate at Cherry Point. And that's in addition to all the studies and all the things you're going to hear about. The committee has a great role in that, and it's very valuable. So if any of that sounds even remotely interesting, I hope it does, we do have a monthly meeting coming up on Wednesday, November 2nd. It's from 3 to 5. It's a Zoom meeting, and I don't know if anyone has access to the contact information right this second, but Hannah, who is new, and we're really happy to have her, she can get that for you, and you can contact her at Resources. So, really, what does the committee do real fast? And that is Well, for one thing, we put on a science forum once a year, which you're here, so you must have some interest, and I'm really glad you are. We also do something called What's the Point, which is going out onto the shore itself with community scientists, naturalists, and getting first up close and personal with the critters that are actually out there and the people who do that. And that's usually in June of each year, and it's fabulous. So I highly recommend, if you haven't done that, to do that. There's a marine bird survey once a month from September through May that I personally participate in every month, and has been an awesome experience. It has enhanced my interest in birds, and part of my participation in the North Cascades Audubon Society, the local chapter here, which I'm giving a plug for very intentionally, and I hope you might find out about that. Whoa, that's a terrible picture of me. No, no, no. Why'd you do that? No, no beard then. Anyway, thanks whoever did that for nothing. Anyway, there's other things too. There's intertidal monitoring. If you are really, there you go. If that's your thing right there, and I have participated a little bit in that, and it is pretty interesting. And there's also beach cleanups. We do a couple times a year. We go down to Gulf Road at Cherry Point and pick up trash, particularly after the July 4th extravaganza that happens down there every year. So, those are kind of the sorts of things. If you are on the committee, you're going to learn about a lot more too. You're going to learn about different types of kelp surveys, opportunities maybe to participate in those sorts of other surveys, more scientific research. The light trap is going on. There's just all kinds of cool stuff that you'll find out about if you're part of the committee. So really, for me, it's, just learning about all the different science studies and that have going on, and really just becoming so much more aware of this beautiful place that I get to live in makes me want to even do more to protect it. And if you are part of the committee, that is something that you'll have the opportunity to do, especially if you know about one of the new things that is coming up with the possible proposed Atlantic salmon facility down at Gulf Road. There could be some very active opportunities there if that sort of thing interests you. I've gone on too long, but protecting this beautiful place is very important to all of us on the committee. And if you are interested, we would be happy if you'd like to check it out and see if you want to participate. Thanks very much for your time. And I'll send it back to Eleanor.
Thanks, Robert. I am going to pass it off to Lyle to introduce our first speaker. Lyle is also on the Cherry Point Aquatic Reserve Citizen Stewardship Committee. So go ahead, Lyle.
Thank you. Yes, well, I've got a quote to start off with. Every time that you wash your synthetic clothing, you shed a little bit of plastic or nanosilver down the sewage, said Iselle Flores Ruiz back in 2017 when she was a University of British Columbia student, currently researching pollutants in the Georgia Strait. 5 years later now, we will hear from Ms. Ruiz on the state-of-the-art science regarding detection of microplastics in the Salish Sea. Iselle Flores Ruiz obtained her Master of Science from University of British Columbia, studying the bioaccumulation of trace metals in the Salish Sea marine food web. Now, as a lab manager at Analytical Science and Analytical Scientist for Ocean Diagnostics, a company in Victoria, BC, she is focused on developing innovative methods to measure and analyze microplastic pollution. She has also coordinated community science volunteers for a local microplastic pollution study in southern Vancouver Island. Iselle is also passionate about engaging with policymakers in order to create regulations pertaining to microplastic pollution in a more efficient way. Mrs. Ruiz's presentation is titled Novel Technology Enables Community Science Microplastics Monitoring on Sandy Shorelines of Vancouver Island. She will explain how technology can help community scientists, such as us on the Cherry Point Aquatic Reserves Citizen Stewardship Committee, how to monitor plastic pollution in their local sandy beaches. Please join Iselle to learn about new tools that community partners can use to collect microplastic data for their area. Iselle?
Thank you very much, Lyle. I had completely forgotten about that 2017 quote, but it still holds true. So good morning, everyone. Today I will be presenting on microplastic pollution. I know the title is a bit of a mouthful, so bear with me, but thank you very much for having me here today at the Cherry Point Science Forum. And yes, as Lyle mentioned, my name is Iselle Flores Ruiz, and I am a lab manager and an analytical scientist at Ocean Diagnostics. And today I'm going to be talking to you about an example of how our novel technology has helped community science basically monitor microplastics. In this specific example, it's going to be about some sandy shorelines in Vancouver Island, BC. So I'll first tell you a little bit about the company that I work for. We are Ocean Diagnostics, and basically our mission is to diagnose and protect our planet from the threats of microplastic pollution and biodiversity loss. And we do this through innovative technology. We have also cutting-edge laboratory capabilities, and we also focus in collaborative partnerships. We work with quite a variety of groups, such as academia, government, industry, different foundations, and also community scientists and community science groups to both collect and analyze data that we need basically to see the future that we would like to see. So to start us off, I would like to basically, introduce you to the idea of microplastic pollution. And the first thing is, what are microplastics? You might have heard that word, and maybe it sounds a little bit scary, but you might not be completely sure what it means. And basically, it's a very broad term. It just means that it's a piece of plastic of 3/16 of an inch for you folks that use the imperial system. Otherwise, it's up to 5 millimeters of length or smaller in size. And these plastics are contaminants of growing environmental concern. Here, I am showing you a picture of a pencil. Basically, when you are thinking about microplastics, you're thinking about pieces of plastic that are either the same size or smaller than the eraser that you find on top of the pencil. So, pretty small. And you may or may not know, but there are 6 main categories. And these are mostly described only by their physical features. So we're talking about shape and also texture. So for example, the first category we have is nurdles. So nurdles tend to be raw material, the raw plastic that is used to create other plastic items. And they tend to be spherical. You might know them from, bean chairs, bean couches. They're full of nurdles. Then we have, of course, tireware. And as its name suggests, they come from the pieces of tire from your tires. Then we also have fibers and lines. These fibers can be coming off of your clothes, but also from fishing nets, for example. We have fragments, and that is also pretty varied, basically just pieces of other plastic that have just broken down. They can be pretty rigid or pretty smooth. We also have foams, mostly polystyrene, and these are very squishy when you touch them. And finally, we have films, which would basically be just very thin, very flexible pieces of plastic. So think about plastic bags or maybe potato chips bag. So cool. Now we know what microplastics are. And I have mentioned this a little bit already, but where do microplastics actually come from? And there are two main categories of microplastics. We have first primary microplastics, and these would be the raw materials, or for example, microbeads. So as I mentioned before, we have raw materials, usually in the shape of nurdles, and they're just easy ways to first create the material that is needed for a plastic item. And at a factory, they will be converted into something else, usually something bigger. We also have microbeads. And these microbeads are basically, they have been created to be that specific size. So you might have heard already about some microbeads ban in beauty products. These microbeads tended to be used in exfoliating creams, sometimes even in toothpaste. And then for the second category, we have secondary microplastics. So these microplastics were not created to be that size. It just happened that these pieces of plastic were broken down from larger pieces of plastic. These tend to be the more common ones to find. And if you can think of microplastics, maybe you start with a large piece of plastic, maybe you're cleaning that up from the beach, and then maybe you missed one piece, let's say, and due to the environment, like the temperature, erosion, wind, or whatnot, that garbage basically just breaks down into smaller pieces, and those smaller pieces could also potentially break down into even smaller pieces. So these are the two main categories of microplastics, and some examples of where they come from would be fishing nets. Fishing is a very important source of contamination of microplastics. Usually there's a lot of fibers, foams, mostly due to boating. The docks and flotation devices all are made of polystyrene. We also have, of course, microfibers, and these tend to mostly come from clothes that we wear. We use a lot of synthetic materials, and every time that you wash your clothes, some of those fibers get shedded out and into your laundry water that eventually gets into the sewage. We also, of course, have plastic factories. If there's ever an unfortunate spill of nurdles, this tends to be where these little beads come from. Of course, every time you drive your car or someone's driving their car, you know, those wheels are going to tear and wear. So that's where tire wear fragments come from. And then single-use plastics are also a very big source. In this category, you may or may not know, but we also have cigarette butts on it. Yes, cigarette butts are also made out of plastic. These fragments can be extremely varied. And finally, one last example would be construction. Again, polystyrene foam is a big one here. It is great for isolating things for different temperatures, or maybe you just have something very delicate and you need something else to protect it, but it ends up, you know, breaking down and causing more pollution. Okay, so now we know what microplastics are, and now we know where they come from. But do we know why they are so? Why are they a pollutant concern? And the reason is that, like, mostly microplastics can be ingested by organisms, right? So this means that the microplastics can accumulate in the body of an organism, you know, insects, zooplankton, fish, mammals, and so on. And because they might accumulate in their body, again, we're talking about something that is not food, right? However, when an organism eats quite a variety of microplastics, I'm not talking just about like one little bit, but, you know, eventually, throughout time, they will probably have eaten a lot of microplastics if they're exposed to them. This might lead to starvation. And why would that be? Well, an organism like a fish, for example, might have eaten something by accident, or maybe they mistook it for a little zooplankton. And they might have thought that they were eating something that would actually provide nutrients to them. However, plastics are not really nutritious for anyone, and they'll accumulate in their stomach and eventually leads to starvation, because their body will think, oh, I have food in my stomach, so I don't need more, or I've eaten this much and I already feel bloated because I already have more things in my stomach. So microplastic ingestion can lead to starvation. Something else that comes from ingesting microplastics is the delivery of toxic chemicals. So microplastics can act as, think of it of a little sponge. So if the plastics are just in the environment, they might absorb any potentially toxic chemicals. And when an organism ingests those chemicals, well, that microplastic that has the chemicals, they might be released into their system. So it might lead to potentially some reproductive issues. And finally, because microplastics are, physical things, we also have that if they spend enough time out in the environment, we'll have microorganisms potentially attaching to the outside of the microplastic. And if an animal ingests these, it could be that those microorganisms will infect in a way the animal. So this is another reason why microplastics are an issue. And now we have all of these issues, that they can absorb toxic chemicals, that they can lead to starvation to animals, and they also can release microorganisms into the animal system. And if you think about it, this might happen to one specific fish. However, that fish is probably going to get eaten by something larger and higher up the food chain. But that animal is not only eating one fish, it's going to be eating many more fishes, right? So as you go up the food chain, it is likely that you'll see a lot more microplastics in the animals higher up in the food chain because of this. So yeah, this is unfortunately how microplastics can have an effect in the environment. Okay, so we've talked about the problem. How on earth do we deal with microplastic pollution? How can we fight it? And as you might already know, or maybe from this presentation you're gathering, microplastics are very difficult to quantify and characterize. And the reason for this is they are small. They tend to be in quite a variety of places. The term microplastic only says, oh, they are this size and smaller, and they're plastic. So you can have so many different combinations of what kind of plastic they are, what kind of which polymer. So is it polystyrene? Is it polyethylene? Is it, I don't know, polyester? And then we also have the issue that because plastics come from many different places, they might have different additives included into them. So it ends up happening that microplastics, there are a lot of them, and they are very varied. And because of this, there are many data gaps in the research. It takes a very long time for research scientists to be able to collect information of where these microplastics are, how many are there, where could they potentially be coming from. And this is where community science can really help us. So today I'm going to give you an example of how community science can help us fight microplastic pollution. And the example that I'm going to be talking about is somewhere nearby Cherry Point, a little bit up north and west. And basically, ODI, myself, like ODI and I were involved in this community science pilot project. We did this in collaboration with Environment and Climate Change Canada. And we ran a community science beach sampling project in Vancouver Island, BC, specifically in the Greater Victoria region. So for those of you who might have visited, we're talking about Victoria, Saanich, and Sydney area. And we had 3 goals for this. The first one was to develop an easy-to-use community science tool to monitor visible microplastics, specifically on sandy shorelines. We also wanted to validate some microplastic imaging tools that we have designed. And we also wanted to test and validate that we were able to analyze and report data consistently for this project. And finally, we wanted to learn where these microplastics were coming from and where any hotspots might be. So we wanted to be able to inform on the resources, the transport, and the eventual fate of the microplastics in the Salish Sea ecosystem. So I won't go too much into detail about the study design, but basically last year in 2021, for 6 months, we recruited over 50 different volunteers, community scientists to help us their data. We had 10 different sites throughout the Greater Victoria region, some in more remote areas, some in, close to the harbor. And these sites were sampled every month, consistently for 6 months. At each of the sites, there were 4 different quadrats tested. So these quadrats would basically be just a square of 0.5 meter by 0.5 meter, and sand would be taken down to a depth of about 5 centimeters. And the volunteers would sieve through the sand and look for suspected microplastics. So basically things that looked like they could be microplastics, but could or could not exactly be that. And every month, I would take those samples and I would prepare them in the lab. And what this meant was basically I would combine all of the identified suspected microplastics from each site, like all the quadrats. So basically put the 4 quadrats together to make one sample and just sieve and clean things through to make sure that what the volunteers had gathered was actually a microplastic. So I would clean the samples, I would separate them a little bit by size, and once we had a clean sample, what I would do would be use the Saturna imaging system that you can see here to your right. And basically, this is a great tool because something that will usually take a lot of time, we were able to cut that time down by a lot. Usually, scientists studying microplastics will have to measure every single piece of every single microplastic they find, and you might it can take a lot of time, more so if you are finding a lot of microplastics. So this Saturna imager, what it would do would be measure basically by taking a picture and scanning the picture. It would measure size, perimeter, area, and how many microplastics you had added to your sample, which made things a lot quicker than it would have otherwise. With this method, we were able to identify 2,426 microplastic particles throughout the 10 sites throughout the 6 months. And one last step that we had was we used something called Raman spectroscopy. And what this tool helps us with is to confirm what kind of material the plastic is made out of. So sometimes it's not sometimes actually, a very important thing to know about microplastics is where they come from. And to do this, it is a good idea to know what sort of specific plastic type they are made out of. This will help us track and understand where the main source of this contamination is coming from. And to do this, again, we use something called Raman spectroscopy, and it basically gives us a specific fingerprint of the material that the particle is made out of. We measured 560 particles, so almost a quarter of the total microplastics identified. This took a couple of months, so microplastics research takes a little bit of time. And finally, we did some quality assurance and quality control on all of our particles, making sure that what we had identified were actually microplastics. We also trained some community scientists to help us confirm what our artificial intelligence imaging system had done for size, and also make sure that the color and the type identified by our system were correct. So what did we find? And this was actually pretty amazing to find, but basically we found that over 80% of the microplastics that our community scientists had gathered were polystyrene. So we're talking about basically just, foam. And as you can see here on the map to the left, you have basically the 10 different sites. They vary on, like the pie charts vary on size based on how many microplastics were found at each specific station. And by how much salmon color there is on the pie charts, you can see that foam was a very big source of microplastic. There were also some fragments and some pellets, but overall it was polystyrene. And more interesting, we also found that the highest levels of polystyrene were coming from enclosed sites. So basically beaches that were that were a little bit covered. And these sites were very close to quite a few marinas. We also compared our results with other studies that have been done in the province of British Columbia, and groups that usually will clean for at the beaches. Basically, they also tend to find a lot of polystyrene, and this is due to how much polystyrene is used for flotation devices in docks, and also for fishing equipment. As part of the results as well of the project, so not the study itself, basically the community scientists were able to identify hotspots in the area, and we were able to do a monitoring program and intervene on the pollution, basically by learning what was going on and finding out where potential sources of these polystyrene were coming from. We also know that long-term monitoring programs are very important because they will give us a better idea of the bigger picture of which places are more vulnerable to plastic pollution. And we also need long-term monitoring to be able to determine the baseline levels. So from 2021 onwards, has microplastic pollution increased? Has it decreased? Has it stayed the same? Have any regulations been established? So it's important to have a baseline level that you can compare to later on. Of course, with the help of our lovely community scientists, we were able to create the most extensive data set on shoreline microplastics in the province of British Columbia. Besides the pilot project, we also had a social media campaign, and we were able to reach almost 1 million people throughout the world. And we engaged over 30,000 Canadians about the microplastic pollution problem that they may or may not have been aware of before. And finally, we also were able to validate a community science toolkit that can help fill that local data gap and be able to monitor microplastics at a larger scale. And it uses very efficient tools that otherwise would not be available. So why have I been talking about somewhere that is not actually the Cherry Point Aquatic Reserve? Well, as you may know, the study site that I'm talking about is also in the Salish Sea, and it shares a lot of cultural habits with Washington State and also Whatcom County. We're both, both sites are in Salish Sea. We both share very popular human activities such as fishing, boating, and tourism. And these activities can unfortunately have an impact on the microplastic pollution in the region. So we know that we have done some studies on the British Columbia side of the Salish Sea, but I mean, the Pacific Northwest is very similar throughout. So do we know what microplastic pollution looks like in other places in the Pacific Northwest? We don't know. So we really need more data to understand microplastic pollution and really identify solutions to this issue throughout the Pacific Northwest. And as Robert and Lyle already mentioned, I know that Whatcom County has already been very involved in fighting plastic pollution with all of the beach cleanups, specifically the one after July 4th. So you already have a lot of the tools needed to do microplastic research, tackle microplastic pollution besides plastic pollution. So how do we do that? How do we add onto the efforts that you are already taking? And one option would be with the Microplastics Community Science Toolkit. So this toolkit is specifically for beach cleanup groups, for schools and community volunteers who want to tackle the issue of microplastic pollution. The toolkit basically has it conducts a study in your community to inform about local research and solutions for microplastic pollution. With this toolkit, you can also test for the presence of microplastic at your favorite beaches and potentially learn about the sources of these plastics and how to diminish them. This toolkit also provides a tool to educate and empower yourself and your community to fight microplastic pollution. And if there's already groups set in place that do beach cleanups and plastic pollution research, we also have advocacy tools so that with any of the data that you can collect from microplastics, you can actually make a change in your community. And finally, with the microplastics that you measure with a toolkit, you can actually contribute to a global database. So just adding into the pool of knowledge of microplastic pollution throughout the world. Very quickly, the toolkit really just has the digital educational resource. So these resources are about microplastic pollution, also about STEM and community science. You also get the basically sandy beach field sampling protocol and sieves, and steps on how to sample and conduct monitoring research in your local sandy beaches. As I mentioned, you also get our technology. So basically, technology that would help you measure quickly how many microplastics you're finding and share that data with a database, a global database. And also with that data, we help you to understand the potential sources of microplastic pollution in your community. And finally, once you've gathered all of this data, if you're interested, you can also help, learn how to engage and help make talk to local decision makers to tackle microplastic pollution and build awareness of this problem in your area. So that would be for the toolkit. The next steps for ODI, myself included, would be to keep contributing to the development of impactful benchmark data on microplastic particles in both coastal and freshwater ecosystems. We are also collaborating with partners to develop different sampling protocols for different other environments. We are helping establish an international network of communities that are monitoring visible microplastic on beaches with standardized tools. It's very important that standardized tools are used because that way you can very quickly compare information taken from one site and another site that might be a little bit different. And finally, we are also expanding this program that is derived from the pilot projects that I have been talking about. And we're expanding the program to different schools and beach cleanup organizations in the Pacific Northwest. So if you learned something about this presentation and you feel very open to add on to some efforts that you all have going, you can connect with us on Twitter, on our website, or also an email, and we are more than happy to help answer any questions. And finally, I would like to thank all of the partners and supporters of this project, especially to all of our community scientists, volunteers. Without all of their help, we would not have been able to make this project a reality. And with that, I'm more than happy to answer any questions you might have.
Great, thank you so much. For those who know me, I love community science, so this all really excites me, and it's good to hear some of the updates because I haven't been able to follow so closely, like that you're able to find, have tools that can better help measure and identify all the microplastics, because that seems like it's been part of the bottleneck in the past is it just takes a long time.
It does.
So I'm really excited that you have a tool for that now. And it's not too surprising, I guess, to me that you're finding foam is one of the largest microplastics out there. I've definitely been to my share of beach cleanups, particularly on like the outer coast areas where there's almost in some areas, there's just like, it looks like a big piece of styrofoam washed up on shore, and then it just fell into all the different pieces of styrofoam instead of being one unit. And then that particular section of beach has almost more styrofoam in it than it does like sediment. So our first question that we have is, and I would remind folks to type your questions into the Q&A. You can also type it into the chat, but first question is from Erica. Thank you for your interesting talk. Do you know whether the results of your findings have been used to inform policy change?
I believe that we're currently working on that. The study is still pretty brand new, but from the pilot project, as we've been able to contact groups that are interested in conducting their own research. So unsure as of now if it has specifically worked towards changing legislation, but it has definitely helped build up into all the pool of data that is needed to change things.
Great, thanks. Our next question is from Lyle, and he asked, is ODI monitoring microplastics nationally or internationally?
Mm-hmm. So ODI provides the tools to monitor microplastics. We are not spearheading any specific projects. The pilot project was an exception, and we are very interested in doing it internationally. Right now, we have actually talked to potential international partners, and also the Pacific Northwest. You know, it's very related. We are neighbors like of BC and Washington State, and we share a lot of things. It's not like the Salish Sea stops at the border, so we tend to have similar issues and probably very similar ways of tackling problems.
Definitely. Which gets to one of my questions is, do you have any, I guess, recommendations for looking at those transborder issues and how we might be able to better work together, whether it's Washington and BC or Canada and the US? Have you seen any efforts recently to work on this? I know I've seen some in the past, but I'm curious if you have any thoughts on that.
Yeah, well, good question. I know, for example, California state is actually spearheading some basically requirements needed to regulate microplastics in drinking water. And it is not only California that is following those instructions. It's actually, from my understanding, it's the first piece of standardized advice that has been published, and I know that at an international level, many people are using it, ODI included. Specifically for transnational, maybe more BC and Washington states, I know that, well, I am aware that there are probably some international efforts. I believe that, for example, the Salish Sea Ecosystem Conference, people from both sides of the border gather together and share a lot of information. So that would be where most of my information is coming from and most of my knowledge.
And then I guess going from the management level of like the much larger scale, going more locally to a place like Cherry Point. You touched a little bit on this, but do you have any recommendations? So Cherry Point Aquatic Reserve is just in the final steps of finalizing their 10-year update to their management plan. And so now might not be the exact time, but maybe there's something we can squeak in, or there's something that we can maybe build towards for the next 10-year update. Do you have any recommendations on how maybe a place like the Cherry Point Aquatic Reserve could implement some management or policy that could better help protect from microplastics or help address the problem so it has less impacts on the aquatic reserve?
Of course. I would say the first thing that you might want to have is data. Policymakers like to see some numbers, for better or worse. So you need to establish first why microplastic pollution is something of concern in your area. Like most people probably already know, because again, as you mentioned, they can see it if they're going to any beach, right? But you need to be able to provide more information to policymakers that can then and basically push forward through data to say, hey, this is an issue, and we are, as a community, we're very interested in fighting this because of X, Y, Z. Something that you can also do, single-use plastics are, they are a very prevalent issue. And if your county has a lot of tourism and so on and so forth, maybe you can push for some, at the very least, single-use plastic bans. So maybe not something at a state level, but community level. And if you're interested in doing microplastic pollution in specific, if you're already doing some beach cleanups, you might want to keep part of the beach intact, like without you cleaning some of it. That'll give you a better idea of what sort of things are actually coming up and maybe where that might be coming from.
Great. I love that answer. Any other questions out there? And I guess I would just do a quick plug for those who are interested in following up on, policy change relating to plastics. The legislative session this upcoming year will very likely include stuff relating to plastics. So please stay tuned for that. And we have passed a few local ordinances in Bellingham relating to reducing single-use plastics, like the reducing the amount of plastics at restaurants, also hotel mini bottles and single-use plastic bags and things like that.
Awesome.
Yeah, and I also, I guess, would mention too, I guess you presenting here today from BC to the Cherry Point folks is, I guess, one of the steps of working cross-border is just knowing what everybody else is doing is an important first step. So thank you. And if there are no more questions, I think we'll move on to our next speaker. Thanks so much.
Bye.
Bye. So moving on from microplastics, which some people consider to be a form of an oil spill, we're actually moving on to oil spills and impacts for that. So I'm going to and also if you're tuning in, stay maybe a little closer to your computer because this one will involve a few poll questions. So be on your toes for that. And without any more, I'll let Lyle introduce our next speaker.
I thought it was me.
Sorry, Robert is introducing our next speaker. Sorry about that.
Yeah, unfortunately, you get me again, but I'll be real quick. It is my pleasure to introduce Raisha Lovindeer. She's a postdoctoral research fellow at the Mesoscale Ocean and Atmospheric Dynamics Research Group, which is a pretty impressive title, Earth, Ocean, and Atmospheric Sciences Department at the University of British Columbia. That's a mouthful too, and very impressive. The title of the talk today is a tool to determine the long-term impacts of oil spills on the marine ecosystem in the Salish Sea. Raisha is a postdoctoral fellow at the University of British Columbia. She holds a PhD in Earth System Science from the University of California, Irvine, and an MSc in Marine Science from Stony Brook University. She's been working on human impacts to coastal waters for the last 15 years, very impressive, including oil spill management and mitigation in government and industry in the Caribbean. Currently, she's in charge of transitioning the knowledge and expertise of the Salish Sea Atlantis model from development to operation. And since our Cherry Point Aquatic Reserve is tucked in next to an oil refinery, I can't think of a more fitting and interesting topic to hear about, and I'm really looking forward to it. So take it away, Raisha.
Thank you very much, Robert, and thank you everyone for inviting me to come and speak at the forum today. I am very excited to tell you about a model that we have been working on from the University of British Columbia. As Robert said, I'm a postdoctoral research there, and so this is my postdoc work that I'll be talking to you about. And it's a tool that we're developing to manage the long-term impacts of oil spills, as I said, in the Salish Sea. And it is a large collaboration with a lot of people because it's a model that's developed on a modeling framework that is already established, but is being implemented regionally in the Salish Sea and required quite a lot of data. And so it is a collaboration with the more long names, the Commonwealth Scientific and Industrial Research Organization, or CSIRO, in Australia, their Oceans and Atmosphere Department, as well as University of Victoria, and then other researchers at University of British Columbia. And I don't necessarily need to introduce the Salish Sea to this audience, but you do know what it is, but because it's recorded, it's still good to point out the region of focus for the model. It's the whole marginal sea that's located between Vancouver Island in mainland British Columbia, Vancouver Island and mainland British Columbia, and the northwest coast of Washington State. And we know it is also home to the Indigenous Coast Salish people and their governments. So there are quite a number of people who depend on the Salish Sea for their livelihood and their habitat, ecological life. But of course, there are also human activities that make a big impact on this area. As Robert mentioned, you're right next to the reserve itself. The Cherry Point Reserve is right next to an oil refinery, and there is a lot of ship traffic that goes through the Salish Sea, especially the Strait of Juan de Fuca and around the San Juan Islands. And ship traffic has been increasing from year to year along these routes. And with that increase comes the risk of oil spills. I believe there was a oil spill close to the Aleutian Islands in August this year, a diesel spill. It's just an example of, yes, smaller spills. Thankfully, the Salish Sea itself has not had very large spills, which we are very grateful for, but we want to plan for what we would do in the event that we do have those spills, and then also to kind of know what would happen to the ecosystem if a large spill were to occur. So many of the studies already in the Salish Sea on oil impacts have mostly focused on the direct or the short-term effects of contaminants. And when I say short-term, I mean within the days in which the spill has occurred and maybe weeks or even months afterwards. When I say long-term, I'm talking about decades and the knock-on effects that can happen through changes in bioaccumulation that might impact the population. And so to do this, we can't rely on just lab or field studies. So what we've done is developed a model for the Salish Sea to try and tackle this problem of the long-term impact of contaminants. And this is a whole of ecosystem model called Atlantis. And when I say whole of ecosystem, what I mean is that the model integrates all of the pressures of an ecosystem and the processes within its framework. So that includes the physical environment, all of the biology and the chemistry, and the human activities as well. It's quite a mammoth of a model. And there have been Atlantis models that have been developed in other places. In fact, there is an Atlantis model for Puget Sound separately from the Salish Sea Atlantis model. The Puget Sound Atlantis model focuses mainly on the impact of environmental stressors on salmon. And so they have a very expanded biological component for their salmon, whereas the Salish Sea Atlantis model incorporates Puget Sound, and their boxes are able to overlap the Puget Sound Atlantis in case we want to do collaboration. But we have included quite a number of other organisms and a larger spatial range, focusing more on the impact of oil. So I will let you know how the model works, the physical structure, the biology that's in the model, how we get contaminants into the model and their interaction with the biology. I'll talk about some of the data that we gather for the model, because as I said, it's a mammoth, so it needs a lot of data, and we'll talk about some of that. And then how we use the model, what we're using it for, and an example of some of the outputs. Okay. So Atlantis itself is, as I said, it represents the whole inland sea area. And you can kind of see that there are these very large boxes that are used to represent the different areas in Atlantis. There are 130 of those boxes, and it does include the islands as well. But the islands are not included in any model calculations. They're just there to depict that islands are there. But the model itself is a marine model, and so the calculations within the model are really for the boxes that are highlighted in blue. And the different colors of blue are showing you all of the different depth ranges. Some of the areas are much deeper than others. And so we just represent that based on the number of boxes within each of the depths. So deeper polygons or regions have more boxes, and then shallower ones have less. And the shapes of these, the polygons themselves, are defined based on geographical traits of the region. Sometimes it is biological traits as well. So if, for example, there is an area that is ecologically significant for kelp, then we'd make sure that all of that area is within a box. If there's an area that has similar flow types and flow regimes, then we'll ensure that in that area, all of that is within a box. And so there's a lot of different data that comes together initially to determine how to create the boxes, and then how to get some of the resolution that we want in different areas. So you might notice that around the San Juan Islands, the boxes are a bit smaller because we try and get those areas have more distinct features from each other than, say, let's say the Strait of Juan de Fuca that has these really large boxes. And so most of the data, as I mentioned, we got a lot of the data from information that was gathered for the Puget Sound Atlantis for the American side, because that model was built before the Salish Sea model. And then citizen science data, as well as universities. And, there's a lot of data collected from the University of British Columbia, as well as University of Victoria on the hydrology of the Salish Sea. The hydrodynamics is taken from additional models. So this is another really powerful part of the Atlantis model, is that it can take inputs from other models. And there are always smaller and more regionally specific models that Atlantis can use, and that is excellent. In this case, the hydrodynamics, and that is all of the movement of the currents and the winds, come from Salish Sea Cast NEMO model, which is a well-established hydrodynamic model that's run out of my advisor's lab at the University of British Columbia. And wind data is taken from Environment Canada. I'm just gonna say HRDPS because, but it's like a high resolution deterministic prediction system where they measure the winds, and we have historic data. So we're using from like 2007 to 2011, 2021 actually. So a full record of winds in the area that we're able to force Atlantis with. So the hydrodynamics is pretty robust within the model. What you might be most interested in are the biology. So there are 58 biological groups in Salish Sea Atlantis. And this is a high number of biological groups, and still it does not represent the full biology of the region. So some of these are large groupings that would have a lot of different species and genera within them, but for the purposes of running a model, we have to cut off the data at some point. And so some of these groups, yes, they contain a large number of organisms, but it's sufficient for our purposes to group them in this way. And so you'll notice that there's both salmon and then other finfish, because salmon is pretty important in the region. And so the salmon group is broken out a bit more than some of the other fish. And most of the biological groups are fish, but we do have, algae. We include birds as well, especially seabirds, because they are part of the marine trophic system, even though they don't live in the water itself. There's plankton, and that includes the phytoplankton, which are the primary producers. They use the sun to produce their own food. And the zooplankton, which are the ones that eat the phytoplankton and carry that energy up the food chain. And then invertebrates all the way up to the larger charismatic megafauna is what we like to call them, the sharks and the marine mammals. And we do represent both the resident and transient orcas, but we don't split them into northern or southern in this case. So a lot of biological groups that are tracked within the model, and also tracked are their trophic interactions. And there are very complex trophic interactions in the environment that we're simply trying to mimic within the model itself. And so this little ring here with the different colors are showing you the the trophic status of all the organisms that I displayed on the previous slide, going from, as I mentioned, the primary producers, the phytoplankton, and all of the macroalgae and seagrass, all the way up to the top predators. And understanding who eats what is also a whole area of data gathering that goes into the model and helps us to understand how the food web works, and so how the model would also work. And you'll understand why all of this information is needed in a moment. So for the contaminants, so we're doing oil spills and oil-based contaminants, and there are many components of oil that are hazardous, and we're aware of this, but the most well-studied parts are the polycyclic aromatic hydrocarbons. I'm just going to call them hydrocarbons going forward. And but even within those hydrocarbons, there are different levels of toxicity. And the easiest way to represent some of the levels of toxicity are to choose representative compounds of oil that have different toxic modes of toxic action and levels of toxicity. And so for Atlantis, we've chosen 4 of them to capture 2 ring compounds, which are light and will quickly evaporate, as well as quickly get incorporated into organisms, but also quickly get metabolized, all the way to the 5 ring compounds. Those are the heavier weight molecular compounds that are sometimes more toxic. And so I've put their names here. Those are the 4 that are built into Atlantis. And then what we do is to be able to model a particular type of oil, we vary the ratio of those compounds based on the oil type that we're modeling. And it's usually a specific oil type. So I have diesel here, but we will know that it is a particular type of diesel from a particular ship when we're doing a spill scenario. And in that case, we will use that oil's data sheet to know exactly what the ratio of the different representative compounds were, and represent that ratio in Atlantis to be able to represent that oil. So diesel has high concentrations of the lighter naphthalene and phenanthrene, and then no benzoapyrene. And so when we're modeling diesel, this is the percentage that we use, versus bunker C that has all 4 and in different percentages and ratios to each other. And this, of course, yes, models are always simplified versions of reality, but this one allows us the flexibility to model more than one oil type and model the realistic impacts of those oil types on the ecosystem. And so, as you can imagine, there are a lot of considerations with modeling ecosystem impacts of contaminants. So the first is, where does the contaminant go? How does it move in the environment? How long does it stay in the water? And that is needed to, as a very first initial step when there is an oil spill that is modeled, you need to know where it goes and how far it spreads and who it will impact. And the who it will impact is the second thing. Where are the species? How abundant are they? And so data on species distribution and abundance is required to know which species will come in contact with that oil and thus have an impact when there is an oil spill. Knowing information about the diet and their prey choice helps us to know who is eating who. In other words, so which organisms got contaminated and then how are they being consumed? Is that contamination moving up the food chain or not? And so that data is also needed. And then, of course, there's the lethal and sublethal impacts of the different types of contaminants that I had mentioned previously. And so for Atlantis, input is through, and I have a whale here, but I'm just using that as a representation of any of the biological organisms, and they will have different input types. So for phytoplankton, input would only be directly from the water column, whereas for other organisms, input might be both direct as well as through predation. So all of those are represented in the model. And when I say direct from the water column, there can also be direct input from sediment, because of course there are some organisms that are benthic, and most of the contamination will go in through the sediment. Atlantis can handle that as well. There's also me and this word, volatilization. Anyway, that's when that is when the oil is evaporated, and then there are organisms that have to come to the surface to breathe. And so it's possible that that is a route of input. Atlantis is not very good at dealing with that, but we are aware that that is a potential route for some contaminants to some organisms. Direct impacts are, there's the direct one that we can see, which is like when birds are oiled, for example, and that changes their temperature and helps them to not regulate properly and leads to mortality. And other organisms that get oiled, and you can see the oil on their skin, and sometimes it does get absorbed in. But there's also the direct impact on their growth and reproduction and their mortality when they come in contact with the oil, and they're very sensitive to the compound that they've come in contact with. And so those direct impacts are built in, as well as their losses. And losses of contaminants are through metabolism, excretion, and I have mortality here as a loss from the food chain, but sometimes that can reintroduce the contaminant back into the water column, depending on how persistent that contaminant is. And so it is a loss, but sometimes not always a loss from the full system. But the main thing we want to look at, as I said, are not necessarily these direct impacts, it is the long-term impacts. And so scaling that up now to the population level and looking at changes in predator and prey interactions because of some of those direct impacts. Maybe a whole population had a serious mortality event because of the oil spill, and how does that impact the organisms that would normally feed on it? How long does that population take to recover if it is that they had a decline in the first place? And so this is the real power of Atlantis. It is carrying that information forward and trying to understand what happens to some of these populations in the long term after an oil spill takes place. And so as you can imagine, as I said, getting into the data is a task. So building the model and calibrating the model is the longest step of creating this kind of a tool. And we are still in this step. Atlantis, the Salish Sea Atlantis is still being calibrated. But what I wanted to show you here was basically how we go through parameterizing the data, given that there's so much data that's going to be needed. And there is a lot of data out there, but it then needs to be collated, put together in the form that modelers can use. And that's not always the easiest thing. And so, data on the uptake, the impacts, and the loss were collected from a number of lab and field studies. And there are a variety of approaches that are used to supplement data needs. So this schematic on the slide here shows an idealized approach for data selection. And it can be applied to all ecosystem models. This is not just for Atlantis. As long as it's a large-scale ecosystem model that uses a lot of data, then this approach works as well. It basically highlights the steps to ensure that these large-scale models are built on the best available evidence. And so the optimal data, that first line is, data that we have that is specific to the taxon we want. So let's say we're looking at Chinook salmon, and we have data that is on a species of Chinook salmon that was taken from the Salish Sea at a time during an oil spill that looked at the impact of one of the contaminants we're trying to measure, let's say naphthalene or phenanthrene. And that's like perfect data. I have an uptake rate maybe, or some kind of whether the organism metabolizes the contaminant. And I'm pretty confident in the data because it's especially done on the organism I want to model. It's giving me a quantitative number that I can put into my model. And so that's optimal and ideal. Of course, we do not live in an ideal world. So most of the data is not in this form. And so in that case, you start moving now away from, let's say, the organism that you are targeting and maybe trying to get to another organism that behaves in the same way, or the same organism but taken from a different location, or potentially a different stressor. So if I'm trying to look at oil contaminants and I really want the impact of naphthalene, but all I can find is data on PCBs instead, then I may be able to use that data to make a good estimate of a parameter to use in the model. And so this is basically how we go about trying to ensure that we can parameterize a large scale model like Atlantis that has so many different groups while still dealing with data gaps. And so now, hopefully you're close to your computer because I want to ask you, if you can tell me, what do you think, which of these groups, out of the phytoplankton, the macroalgae, the invertebrates, the fish, or the marine mammals, had the most data that was available for us to use? So this is quantitative data. You can go ahead and make a choice. And if you missed the phytoplankton or the little primary producers that take the sun and make their energy and pass it up the food chain, macroalgae are, you know, the kelp, the seagrass, invertebrates are your crabs, and so on. There's a nice list to help. All right. So I think everybody has answered this one. So let's take a look and see. All right. So most people think that am I seeing this poll correctly? Let's see. Yes. Okay. So most people are guessing that they're the most available data for fish. I should write this down. So fish first, and then the phytoplankton and the marine mammals tie for most data. Okay. We'll soon tell you if you're right. So I want you to know, for the same set of groups, I want you to try and guess which group had the least available data. Answers coming in rapidly. This is least available data. Give a couple more seconds. Anybody that walked away from their computer and is madly dashing back. All right, so let's see the answers for this one. So we think the macroalgae had the least available data, followed by invertebrates and marine mammals. All right. So let's take a look and see, how did you do? All right, so for most available data, if you said fish, you are correct. The most available data is for fish, and that is mainly because, I mean, especially commercial fish, right? Fish are consumed by humans, and so we have an active interest in trying to know whether there are contaminants within an organism or not for the fish. And so a lot of testing goes into fish species, and there is quantitative data on a lot of different organisms that we can use. Even if we don't have the exact data on the species of fish that we want, there is so much data on fish that we're fairly confident about the data that goes in for fish. So yes, fish has the most available data, and I made it easy by just lumping them all together. I didn't say salmon or herring separately, but let's see. And for the least available data, I think the major guess was macroalgae. In this case, if you said marine mammals, you're correct. So the thing is that for marine mammals, there are ethical restrictions and concerns surrounding experiments dealing with contaminants. So it's actually very difficult to conduct any kind of experiments with marine mammals. And so most of the data that's collected on marine mammals are opportunistic. They are during times of an oil spill, when, let us say, there is a marine mammal stranding, and then there is the opportunity to test the test the tissue, or to do an autopsy on the animal. There are also methods of going out on a boat and taking dart samples, and that's usually when just a small amount of tissue is extracted from the animal and able to be tested. And of course, that does require a good amount of funding, as well as scientists who are well trained to conduct that kind of test. So things like uptake rates, and I put the units here because this one is one of the hardest ones. You're trying to find a concentration of contaminant over a particular area of, let's say, muscle or tissue per second. And so this is the kind of thing that requires a lab experiment and is not very easy to conduct with marine mammals. So there's the least amount of data on marine mammals. For those that guessed anything else, the macroalgae, the invertebrates, and so on, you're not that far off, because the data on some of these others fall in between the wealth of data that we have on fish and then the paucity of data that we have on marine mammals. Phytoplankton, they do, again, are easier to grow. And so I can understand why guessing that they might be, that there might be a lot of data on them would actually be a good thing, right? Because you can grow them really quickly. You can probably get uptake rates. And I put phytoplankton on the slide, but if I had put zooplankton, then the uptake rates, we do have a lot of available data for uptake for zooplankton because they're feeding on the phytoplankton. But for some reason, the phytoplankton data is not as available. And so there's the data that goes per organism. But then if we look across the slide, we can also see processes that tend to be more data heavy than others. So for example, bioaccumulation within the species seems to be something that is a lot easier to test, mainly again, because you can test for tissue and see whether there is the accumulation of a contaminant in the tissue even long after a spill has occurred. And so there tends to be quite a lot of information on the bioaccumulation of contaminants, as well as maybe on the impacts. And I grouped lethal and sublethal effects here, just to give these organisms the best chance of having the most available data. But in the model, I do have to split it out to know the difference between when a compound is lethal to an organism versus when it reduces growth but doesn't actually lead to death for that organism. And so going back to this scheme, now you kind of understand why this is needed and why the data selection step is very important. And actually, we just as a group submitted a paper about this issue of scoring the confidence of data that is used to go into ecosystem models, so that the user, the user, or the end user, when we're presenting the data to you, can have confidence in the data that is being presented based on the data that went into the model in the first place. And so when you know that we had a lot of data on fish, but we didn't have that much data on marine mammals, when I'm then presenting this, the results of my study to you, then you would also, we would be able to caveat the fact that we had to make a lot of estimates for the marine mammals, whereas we didn't have to make that many estimates on fish. So that's the kind of example I'm talking about. And but having a quantitative measure, so that it is not just about us saying that, well, I didn't have that much data, you can actually see how much data we had and how much data we didn't. So we think that that increases the confidence in the models. Also, the kinds of studies and the data roundup helps to inform research direction. So in the case of the Salish Sea Atlantis model, we're pulling together data from, as I said, a lot of different institutions and organizations and databases. And so it was a perfect opportunity to highlight some of the data gaps so that experimentalists and ecotoxicologists, when they're ready to plan their experiments and they want to know, well, what hasn't really been studied? What is there that is left to be known? This helps a great deal in highlighting some of the data gaps and helping scientists to know where to put their efforts into generating more data that can make models more robust. And so now that you kind of understand how the model works and the wealth of data that goes into it and how we even rank and create the data for the model, what do we use it to do? And knowing what the model is used for is another very important step. So the main purpose for the Salish Sea Atlantis model is risk assessment and strategic planning. And this is ahead of a spill. And I stress this because if you take a look at those boxes, those polygons, they are very large. And so there are two cores to be used for active incident response. And so Atlantis is not built for that. It is not built for when there is an oil spill on the ground, what is it, where is it going to go and who is it going to impact? That is not the power of this model, and it cannot handle that immediate kind of prediction, but it is used for risk assessment and strategic planning ahead of a spill and is scenario based. So we'll come up with a scenario and explore that scenario far into the future, running different variations on that scenario in the model to be able to give predictions or probabilities of impact. And as I said, knowing what a model is used for is an important step because a user must always know a model's limitations so that they don't use it inappropriately and get the wrong results. And so the scenarios that we have used, that we are developing, well, the scenarios have been developed that we will run with Salish Sea Atlantis, have been developed in conjunction with Transport Canada, Environment and Climate Change Canada, and the Department of Fisheries and Oceans in Canada. I'm in Canada, so most of this is coming from Canada. One of the spill scenarios is a very common one, and this is, a dilbit tanker that is trying to make a turn at turn points around the San Juan Islands, misses the turn and hits into Arachne Reef instead and spills 2 liters of dilbit. So that is an example of one scenario. We're going to call that scenario 1. And a second one is, a bulk carrier leaving Vancouver Harbor, losing power, so not able to navigate and colliding into another bulker, spilling a known quantity of bunker C, in this case, 15,000 liters. The quantity is important. Again, it is a quantitative model, so we usually are doing quantitative assessments based on the amount of oil that was spilled, which oil was spilled, where was it spilled. And then, as I said, we can then use Atlantis and the contaminants within to model the different oils based on the 4 contaminants that we have here. So the ratio of the contaminants in dilbit is different from the ratio of the contaminants in bunker C, and we can use those ratios to implement these spill scenarios and take a look and see what the impact of these scenarios are. And as I said, for step 1, the first thing is to know, where does the oil go? And I had mentioned that Atlantis is very powerful in that it takes the input from other models and can use that input in its scenarios, in its simulations. And in this case, we use a Lagrangian tracking model. That just means it follows the particle all the way from the point of release to the endpoint to be able to tell where the oil would go once it is released in the environment. And I use the Ocean Parcels Toolkit to do this. The reason we have a separate model is that we want to know on a smaller time step than Atlantis would give us, where the oil would go, let us say within 10 days or so. You know, where would the oil go? Is it being evaporated or not? And how much of it gets to each of these different areas. And then we then translate that output into the Atlantis boxes. And so now you would just see boxes highlighting to show where the oil is in terms of the Atlantis model domain, so that we can do the next step, which is to figure out which organisms come in contact with the oil during the time of the spill and propagate that forward. Propagating it forward now again, so this is the time component. And as I said, Atlantis operates on the scale of decades. And so initially, there is some model spin-up time, and this is time where the model gets to stabilize and fully calibrate the ecosystem prior to being stable. So this is the pre-spill. Then there's a time when we inject the spill, and I mean, this time is not to scale because you wanted to actually see where the spill is. The spill would probably happen in a day or in 2 days or over the course of 2 weeks. And then what happens post-spill? And post-spill for us is 20 years at a minimum in the future and going forward. And the important thing here is to compare it to a baseline that doesn't have the oil spill in it. So it has the exact same parameters and environment for the model spin up, and the pre-spill environment also propagated to the same time period. And the reason we do this is that there are many environmental factors and variables that might cause a population to decline or increase. And we want to know which of the variations that we're seeing in a population are directly related to the spill. And so when we run the no oil baseline and then we run the spill scenario, the difference between those two model simulations is the consequence of the oil spill scenario only, because that's the only difference between the two. That's the only input difference between the two models. And so that helps us quite a great deal of removing all of the background, I will say noise in this case, but it is all of the background influences on the ecosystem, and only focusing on what we want to know, and that is the impact of an oil spill. And of course, we care mostly about the biology and which of the biological organisms get affected. And there are many, many groups in the model. So which group do we focus on? You know, I mean, if I'm going to present the results of an oil spill, if I'm going to present all 58 biological groups to you, that may not be very useful for you. Maybe you only care about the orcas, because that is the organism that you're studying or invested in. And there are a lot of different organisms within the group, within the model. And so we can hone in and take a look at what the different organisms are based on our audience and based on the public and their interest. And we actually do have a knowledge broker on our team, and that is also her postdoc research, is to go to groups and understand what organisms are most important for you, so that when we are presenting our output, we can tailor that to the audience that we're speaking to. And this does include quite a number of indigenous nations. So as I said, there are people who might be interested in orcas. Salmon, of course, is another major one. As I said, we have broken out the various types of salmon. There's Chinook, there's coho, there's a Fraser River salmon, and then other salmon is pink salmon and so on, because there are people who would want to know specifically about a particular group. And I must point out that this is not only for when communicating output. There was quite a lot of community consultation initially about deciding what organisms were to be pulled out in the model in the first place. And so the same groups that we would want to communicate the output to, there was quite a lot of discussion with these groups initially to find out, well, what organisms should even be in the model in the first place, because you might be interested in knowing specifically what the impact to this organism is going to be in the future. And I'm going to show some example output. This is example because, as I said, the Salish Sea Atlantis is still in calibration, and so we have not run the scenarios to be able to have our own output just yet. And so what you're going to see, or what you are seeing now, is the output of the Gulf of Mexico Atlantis model that simulated the Deepwater Horizon oil spill, showing some taxa that were specific to them and their region. So this is a group of fish, and I'm just showing you the kind of output that you would see. So the baseline that I pointed out is basically at the top. That is the baseline run, and we're only looking at the difference between that baseline and then when we actually run an oil spill scenario. That dip in the initial dip in some of these organisms was the impact of the initial spill, and then you can see that they're recovering over time, with some recovering much faster than others. And as I said, this is the kind of output that Atlantis would be able to show for the Salish Sea as well. The Deepwater Horizon spill was a wellhead blowout. It was throughout the water column. It wasn't just a surface spill. And so there was quite a large impact on the organisms. We may not expect this kind of an impact on the organisms within the Salish Sea from the scenarios that we're running, but this is still an example of what you would see. And then the variation that you're seeing in that gray line are differences in model parameterizations during the run. And this is to account for differences in surface winds and currents during a time when we're running the scenario. So when I was sort of showing where the oil goes, it's important to know that the oil is going to go somewhere different depending on what day you run the model, because the winds are blowing in a different direction or the currents are a different speed and so on. And so what we tend to do is do the scenario over different environmental conditions so that we have confidence in, on average, where the oil would go. But also, if you wanted to know in a specific environmental condition, when the wind speed is very high, or the currents are going in a particular direction, or this is a very high tide, where will the oil go? That would also be included as the data that we're able to communicate. And so I've been talking about oil-based contaminants because that is what Atlantis was built to do, but it is a risk assessment model that can actually look at other stressors and not just oil. So built into the model are also heavy metals. Currently, there is both copper and mercury. However, the model is not yet calibrated to be able to run these scenarios. In other words, we still don't have all of the data on the impacts of these heavy metals on the organisms to simply run a scenario on heavy metals. But the infrastructure is there so that if there were to be a project that would spin up and the associated funding of that project, we would be able to then get the data to do the parameterization and run that scenario. Similarly, we can look at the impact of climate change, which a lot of people have suggested, requested, asked about. And that, changes in sea surface temperature going into the future and changes in acidity as a result of climate change. That is a key question that Atlantis can answer. And this is something that can happen, unlike the heavy metals. We can use the current calibrated model once it's complete to answer these questions, because impacts of temperature and acidity are built into the ecosystem. And so that is not something that is a side project that had to be incorporated in the main model. And so we can then look at climate scenarios in the same way that we look at oil spill scenarios and have some measure of the impact of these scenarios on the species. Again, against the no oil baseline. And in this case, there would be a no change baseline. That one would be harder because we would have to select what the baseline is, but there is always some baseline against which we can examine the data. So in summary, the Salish Sea Atlantis model is a risk assessment tool that's used for strategic planning ahead of whatever scenario you're trying to model. In this case, it is the impact of oil spills. It does represent the whole ecosystem of the Salish Sea, and it includes 58 biological groups, as well as all of the physics and the chemistry of the seawater. It does incorporate quite a lot of data, lab and field data, and you can always reach out to me. If you are in contact with people who generate data, we're always talking to those who can help us to get some of those areas where the data was not fully fleshed out, a little more fleshed out. And we can examine not only the impact of oil spills, but also the impact of other ecological stressors on the environment. And so I'll leave this slide up as we talk. It does have my email on it, so that if it is that you don't get a chance to ask your question today, or you're not physically present at the forum, that you can always reach out to me by email and we can have a discussion about it. Thank you.
Thank you so much. That was a really great presentation, and having done a very simplified model myself of risk assessment modeling, I really appreciate this huge model. There's so much data that goes into it, and thank you for explaining it so well with all the uncertainty of like the quality of data or just how much data you have to inform it. So thank you. So the first question Lyle had was, is industry and or government in the Salish Sea using this modeling?
Right. So as I said, the model is in calibration at the moment, so it is not in operation. That's part of my project, is to get it to the point where we're actually using it in operation. And at the moment, the people most invested are the government of Canada and then the Coast Salish governments. So I believe we may have some industry partners, but I'm not quite sure. I could check our knowledge broker and get back, but nobody's using it at the moment, no.
And if folks have questions, please, oh, there's another question. Please do type them into the Q&A or the chat box. So the next question from Lillian is, does the Atlantis model incorporate climate change and oil spill runs? Example, for 20 years post-spill, there will be some changes in temperature, ocean acidification, etc. Does that make sense?
Yep, completely understand the question. So you basically want to know if in our baseline run, we're taking advantage of the fact that we know that the climate is going to increase going forward. And the answer to that is yes and no. So we are doing sort of an average projection of what has happened in the past and propagating that forward, but we are not doing the projected increases based on emissions. So we haven't incorporated any of the climate scenarios going forward, but we have incorporated the fact that the temperature will increase based on the increased temperatures in the last 20 years. And that is in the base run, and so it's included in the oil run, yes.
Thanks. Going back to uses of the government or other entities using the modeling, in Washington State here, we have geographic response plans that sort of use stuff like this. So I'm hoping that that might be incorporated next time they update those geographic response plans, where they take the US side of the Salish Sea and I think the outer coast of Washington State and look at specific regions. And if there was an oil spill to occur here, what areas might we want to protect first? So one question that I have is, it seems like this is, I'm just looking for a little bit of clarity. Is it mainly focused on like marine water, or does it include shorelines as well?
Oh, that's an excellent question. So the boxes are large, and so it is only looking at marine water. We can't yet give enough information about the shorelines based on the boxes we have. We would be, the only way we'd be able to do that is if we had more information about the coastlines and then we created smaller boxes along those coastlines. So as it stands now, we can't talk about the coast. And in fact, in Atlantis, there is a steep drop off between land and water. And so anything that is intertidal, we can't give any information about that. So that's one of the limitations of the model. Really happy you brought that one up.
Yeah, maybe someday. That's really, as I mentioned before, it's a really complicated model. So it's
Yeah,
great that like waterways are a great place to focus for sure. In your putting together this model, I recognize like it's not totally finished yet, but are there some major ways that we could reduce risk through management and or policy, whether it's at Cherry Point specifically or greater Salish Sea wide? Are there specific takeaways from this model that maybe you're starting to see?
so in terms of risk assessment, I would say not really, because we haven't been able to run the scenarios yet. The point is really to be able to identify areas that are potentially very important to the ecosystem if an oil spill were to occur in this area. And we do want to get to the point where that does inform policy, because the reason that the government of Canada is interested in this is knowing which routes basically are, I wouldn't say at capacity, but basically in terms of their risk to the environment, they shouldn't necessarily be scaling up either the amount of oil that passes through there or the number of ships that pass through there. And so without running the scenarios, I wouldn't yet be able to say what we found, because we haven't found anything yet. But in terms of the data, I think that because we have such a low amount of data on the larger organisms, the mammals and the sharks especially, and especially because the Salish Sea is home to these migratory species that come into the Salish Sea for particular periods of time to either spawn or feed. I think that focusing on getting enough data so that we can really understand the long-term impacts on those organisms might be something that is important and could be an area of future research, but that's as far as I can go with the data that we've collected so far. Yeah.
Great, thank you. And I know the Cherry Point Aquatic Reserve Citizen Stewardship Committee definitely looks at how many ships are coming in and out, and with an eye to, you know, the more ships there are, the greater the risk involved for sure.
And you know, I will mention too that there was a oil spill research conference not too long ago where I presented the model, and there was a representative from Washington Department of State that was very interested. I think maybe something that the group could do, or just citizens in general, is if they know that these tools exist, but that their governments are not necessarily using them, then that could be a point of sort of spreading awareness, because as I say, most of the data and most of the people who plan to use the model at the moment are Canadian. And so it would be nice to actually have the collaboration with the US as well, because it does cross the border. It is dealing with the whole Salish Sea. And I am working closely with the group that runs the Puget Sound Atlantis, and that is run out of NOAA. And so there is that collaboration, but in terms of US government, not really. So that could be something that could be strengthened.
Yes, and thank you so much for creating a model that goes across the border and doesn't just stop
Right.
at Canada. We greatly appreciate that.
The species don't stop, so.
Exactly. Are there any other questions? All right, well, thank you so much. That was a wonderful presentation. We have 2 more speakers coming up, but first we're gonna take a bit of a break. So feel free to go and get lunch, go for a walk around the block, stretch, whatever you need to do, but be sure to meet back here at 12:30. All right, thanks so much, folks.
Jessi enjoys a good cup of tea and warm sunny days above all else. They will be presenting about kelp. Alrighty.
Thanks so much, Hannah. That was a great intro. And thank you to Eleanor and the rest of the folks with the Cherry Point Aquatic Reserve for inviting me to talk with you all today. Get my presentation going. All right. Wait for this load. There we go. All right, like Hannah said, my name is Jessi Florendo, and I am the Habitat Program Coordinator for the Puget Sound Restoration Fund, where I work on both our oyster and our kelp projects. I have the pleasure of speaking with you all today about kelp in Washington State. It sounds like we've got a very macroalgae afternoon for you all going, so I'm very excited to talk to you about some marine plants. I'm really thankful for the entire committee for inviting me to discuss kelp with you all today and connect more people to this wonderful world of kelp forests and restoration. I want to say now that this presentation was made with the guidance and displays all of the hard work of the entire Habitat Program team at Puget Sound Restoration Fund, including my coworkers, Brian Allen, Hillary Hayford, and Greg McKenna. A lot of the work and research I'll be talking about was made possible through the collaboration and advising of our many partner organizations. I'll be sure to mention a handful throughout the presentation, but I'll be sure to include a list at the end for anyone curious. Before I begin, I do want to recognize that I am speaking to you all from Coast Salish lands, which touch the shared waters of the Duwamish, Muckleshoot, Suquamish, and Tulalip nations. I have the honor to speak with you all who protect, steward, and care for Kuchiachin, which is the Lummi word for Cherry Point, home of the Lummi Nation, Nooksack Indian tribe, and other Coast Salish people. As this presentation will focus on kelp, it's important to recognize that kelp is part and parcel of the Indigenous story of water and land in this country, making it necessary to acknowledge and continue to learn about this resource as part of the greater history of where we find ourselves today. To tell you the story of kelp in Washington, it's important to start at the very beginning. We'll begin with what are kelps, discussing what makes a kelp distinct, how are they identified, and which types we'll be focusing on in this presentation. From there, we'll explore the many different functions of kelp, from their ability to create habitats, to their connections to other species and people, to what role they play in human history. I'll lead you through why kelps matter and why it matters that they matter. Finally, we'll discuss how to conserve kelp, covering both what efforts my organization is doing and how you can get involved with kelp restoration. I'll talk broadly about all the things we can do to make sure that kelp is around for many, many years to come. Before any of that though, who am I and why am I speaking to you today? Like I said, my name is Jessi Florendo, and I'm the rain-protected camera avoider on the far right in this photo. I have a bachelor's degree in marine biology from the University of Rhode Island, just a small ways away from here. After I graduated, I moved to Seattle to pursue a Master of Marine Affairs from the School of Marine and Environmental Affairs at the University of Washington, Seattle. Graduating from grad school, I joined Puget Sound Restoration Fund as the coordinator for our habitat program. What you see in the photo is myself and two members of my team working at one of our intertidal field sites for Olympia oysters. The PSRF habitat program includes both Olympia oyster and bull kelp restoration. Although I won't get a chance to talk about our other line of work today, you can always find out more information about all of our programs at restorationfund.org. All right, with all that covered, let's dive right in. What exactly is kelp? Kelp are a type of brown macroalgae, which is also known as phaeophyton. Macroalgae is just one way of saying seaweed, so if you hear that term, they mean the same thing. They are within the order Laminariales, and macroalgae are plants, but not like terrestrial plants. Terrestrial plants are vascular, meaning they have roots that take up minerals and nutrients from the soil and deliver it to the rest of the plant. Macroalgae are non-vascular, so although they look very similarly to terrestrial plants, Their parts serve different functions. All kelp have the same structure. Looking at the picture of the right, you're looking at bull kelp from one of our experimental enhancement sites. Those finger-like appendages that look like roots on the bottom are called holdfasts. Holdfasts attach the plant to their preferred substrate and keep them rooted in place. Connected to the holdfasts are stipes, which are analogous to stems in terrestrial plants, in that they mostly just provide structure. From the stipe, you see in the picture a distinctly round structure, which is known as a bladder. Although these can take different forms across the different kelp species, all bladders are hollow and filled with gas to help the plant rise towards the surface. It's where the light is more available, aiding in their photosynthesis. Finally are the blades, which look like leaves. Although they are the site of photosynthesis like leaves of terrestrial plants, the blades are also where kelp take in nutrients and minerals from the water, which is that main difference from vascular plants. I want to note here that while all kelp are brown algae or brown macroalgae or phaeophyta, not all brown macroalgae are kelp. I listed 2 examples here, which are common nearshore kelp species you may be familiar with or have seen along beaches and coasts without even realizing it. There are many, many types of kelp, and these many types of kelp are found all over the world. 2 researchers, Jessi and Costello, in 2020, estimated that the kelp biome occupied 1,469,900 square kilometers of nearshore habitat, and that kelp were found on 22% of the world's total coastline. While there are a lot of kelp in coastal ecosystems worldwide, there are a lot of kelp here in the Northeast Pacific. In fact, the Pacific Northwest region has the highest kelp diversity in the world, meaning that our waters have the greatest number of taxa within that order of Laminarialis. Kelp species within the Puget Sound are depicted in that inset graphic, which is an artist's rendition of taxa found within the sound in particular. You'll notice a diversity of shapes and forms that kelp take, differing in height, number of blades, yet still having that same basic structure. You'd think in this line of work there'd come a time where I would cease to wonder at all of the kelp we encounter in the field. But the 2 pictures in the background, both taken by me during intertidal surveys in Squim Bay, no more than 5 feet from each other, show the diversity of species and kelp morphology that we have to show in our state. Beyond the different taxa of kelp present in our region, there are different ways of identifying kelp. The graphic from Tom Mumford, who is a phycologist in Washington State, depicts 3 categories of kelp, which are separated by which layer of the canopy they grow into. The lowest lying kelps on the bottom of the seafloor there are called prostrate kelp species, which grow just below the stipitate kelps. Both the prostrate kelps and the stipitate kelps make up the understory of kelp assemblages. They are exceeded only by floating kelps, which are called such because their blades reach the surface and float along the top of the water. Floating kelps comprise the canopy, which will be the main focus of this presentation. There are 2 Washington State canopy kelp species, Macrocystis perifera, which is the giant kelp, and Nereocystis lewickiana, which is the bull kelp. Though both these plants have the same general characteristics that I had described before, they look very distinct from one another. Macrocystis, the giant kelp, have blades that grow all along their height, protruding from individual bladders along their stipes, from lower in the water column up to the surface. Nereocystis, on the other hand, has one long stipe which connects the holdfast to a single bladder, the point from which many blades grow out of. In our surface surveys with bull kelp, we have counted anywhere between 11 and 36 blades on an individual plant. Macrocystis and Nereocystis differ as well in the life stages they have. Macrocystis sporophytes, or the versions that we recognize as plants, are perennial, meaning that mature plants can be found in persistent kelp beds around the year. Nereocystis sporophytes, on the other hand, are annual or semi-annual. This means that kelp beds tend to have a seasonality. In the Puget Sound, kelp sporophytes settle along their preferred substrate and begin growing around early to mid-February, reaching maturity around June or early summer and persisting until fall. Their exact seasonal growth patterns tend to vary across sites, so it's hard to prescribe one distinct pattern of growth. Growth for both canopy kelp species are also impacted by diverse environmental conditions, some of which we'll get to later. Macrocystis is found within the Strait of Juan de Fuca, as well as along the outer coast, as seen here. Nereocystis, on the other hand, is found both in the strait and along the outer coast, as well as within the Puget Sound. Canopy kelps provide a number of ecological functions, but perhaps most notable among them is their role as habitat engineers, creating well-known and well-loved ecosystems known as kelp forests. A kelp forest is a dense assemblage of canopy kelps, often in addition to other understory kelp species. The canopy kelp create distinct habitat and protection from other animals, earning them that title, habitat engineer. They're also known as foundational species because their functions in the water enter the utility of so many other organisms, playing a strong role in structuring community and are highly valuable for that role. These differ from what some folks might know as keystone species, which you can think of like a sea otter, because while keystone species play an important role in food webs and interactions, foundation species are necessary for the community to form and thrive. Other examples of foundational species would be corals in the case of coral reefs, as well as different seagrasses and seagrass meadows. Here. Now that we have a sense of what kelp is, let's discuss why we care about them. Firstly, as previously mentioned, canopy kelp are habitat engineers. Kelp forests are such unique and important habitats. For one, they create nurseries for other organisms, or habitats in which juveniles of species can grow more safely than in other nearby habitats. Other nursery habitats include like eelgrass beds, which we do have in Washington, and salt marshes and mangrove forests, which we don't. The reason kelp forests are effective nurseries are because they buffer against physical changes in the water column, such as strong oceanic currents or turbulence that results from storms. Additionally, kelp forests create ample hiding space from predators, so juveniles can stand a chance to grow bigger and eventually fend for themselves. Kelp forests in Washington waters create habitat for a number of different fish, echinoderm, and crustacean species. Two I want to note, kelp forests are the preferred habitat of rockfish and pinto abalone. In Washington, some rockfish species are listed as endangered or threatened under the Endangered Species Act. Their recovery is regulated by the National Oceanographic and Atmospheric Administration, NOAA, who conserve and protect habitats important to these groundfish, which includes kelp forests. The other one, pinto abalone, are the only abalone species in Washington waters. Although they're not officially listed as endangered, this iconic species has had a near 98% decline from 1992 to 2017. Protecting at-risk species must include protecting their habitats, so the protection and longevity of kelp beds is just as important. Kelp forests are more valuable than just the habitat they create. In fact, kelp directly are a source of food for some grazer species, including various amphipods and kelp crabs like those two pictured here. Although I'm personally biased against kelp crabs because they're only good for a jump scare when you're doing a surface survey, Kelp crabs are an important source of food for a number of predators, including sea otters. As a source for grazers, kelp make up the bottom of extended food chains. These trophic cascades connect primary producers like kelp up to higher order predators, which include charismatic species like salmon and orcas. Salmon feed on forage fish, which are attracted to kelp forests for easy prey items. One of these is herring roe, or the spawning eggs that are laid directly on kelp, which I'll discuss in a slightly different context later. Forage fish congregate in kelp forests for these easy food items, which then draws migrating salmon into the habitat. Although salmon never directly take advantage of the nursery aspects of canopy kelp habitats, salmon restoration practitioners highlight kelp beds as an important ecosystem for long-term salmon recovery and success. And where there are salmon, there are orcas. The southern resident orcas that reside in the Strait of Juan de Fuca are characteristic to the natural identity of this region. Conserving and protecting this population is a priority of environmental regulators and the general public alike. Because the critical habitat identified by NOAA includes both their home in the Strait and the Puget Sound, and their connection to salmon and other hunted fish species, kelp forests are an undeniable link in the southern resident story. Primary producers serve more roles than just as a source of food. As photosynthesizers, kelp use light from the sun to transform carbon dioxide in the water into oxygen and glucose, or energy. They contribute to the global carbon cycle by fixing carbon in the form of carbon dioxide. One unique function kelps conduct within that carbon cycle is actually acting as a carbon sink. When kelp plants die off, their organic material can be broken down by microorganisms in the water into a form called recalcitrant dissolved organic carbon, which sinks to the seafloor. How effective of a carbon sink kelp is being heavily researched today because a lot of people are interested in it as a potential climate mitigation strategy. Additionally, one of the byproducts of this process is oxygen, which is released into the atmosphere. For the folks breathing along at home, there's a chance that your next breath comes from a photosynthesizing kelp plant. In fact, researchers have found that almost every other breath you take is from marine photosynthesizers. Although this category includes all seaweed varieties, algae and macroalgae, as well as phytoplankton, canopy kelp contribute to that total percentage. Kelp are so efficient at photosynthesis and creating energy to sustain themselves that they can grow incredibly rapidly. In fact, canopy kelp are capable of growing up to 10 to 12 inches in a single day during their growing season. Beyond their ecological functions, kelp is significant to people in more ways than one. The kelp highway hypothesis is a collaborative theory from a team of archaeologists and marine ecologists to suggest that kelp forests played a significant role in the dispersal of people by sea rather than by land. Kelp connected people from very early times in human history, to the point of guiding migration through kelp-dense nearshore ecosystems, where food to hunt and to gather was abundant. Kelp is embedded in the histories and stories of Indigenous people in Washington. The figure in this picture on the left comes from the Coast Salish tale of Kokwal-Alut, a woman who married a man from the sea to ensure that her people would have access to resources from the ocean. She began to transform into someone from the sea herself. So when Coast Salish people see the blades of bull kelp that have become her hair, as pictured here, they'll know that Kokwal-Alut is continuing to provide for them. Besides its role in Indigenous stories, kelp is central to traditional ecological knowledge, or the knowledge of the natural world that comes from experience living with and stewarding to these ecosystems since time immemorial. Indigenous tribes in Washington realized the utility of kelp in hunting and collecting food, as well as guiding navigation and being able to be crafted into tools and vessels for any number of uses. If you're interested in these topics, I highly recommend checking out that citation I have listed here, which includes the many different stories and example of kelp's place in the history of people, water, and land. Kelp serves people in additional ways. It's not just other marine organisms that look to kelp for food. Coast Salish people would collect herring roe, or those spawning eggs that I mentioned earlier, that were laid on the kelp directly. That was an important food system for them. Many tribes would also know to hunt otters, as well as the fish that linger among the forests as a safe habitat. Kelp itself is edible as well. Although the commercial kelp cultivation industry isn't well developed in Washington state, there is one farm called Blue Dot Sea Farm that actively grows and harvests kelp to produce food for human consumption. Other farms are starting to take up, catching up with the industry that is well developed throughout the rest of the country. Kelp is found in more products than you might expect. On our team at PSRF, we're big fans of the Bull Whip Kelp hot sauce with peri peri peppers from Barnacle Foods, but we've tried everything from kelp puffs to kelp pickles. An emulsifying agent derived from kelps can be found in some ice creams, as well as in toothpaste. Many skincare companies use seaweeds in their products because the bioactive compounds act as good humectants, which is helpful in cleansers and in moisturizers. Finally, commercially produced kelp are broken down into additives for terrestrial farming, creating both animal feed supplements and soil amendments to support healthy growth. Humans value kelp for more than just its direct utility. Kayakers, divers, paddleboarders, boaters, other recreational watergoers appreciate kelp forests as a unique feature which to encounter, often as sites where people can expect unique sea life or simply to observe the mysteries beneath the waves. There is an aesthetic beauty which all people can love and enjoy. Every function we have covered so far proves that kelp is invaluable. Since the early days of human history up until today, kelp has served people, marine life, and its ecosystems in ways that we are continuing to discover and fully appreciate. It would be in all our best interest, then, that kelp forests stayed around and stayed healthy for a long time. Unfortunately, that's not the case. In Washington, we have seen significant declines in kelp beds from their historic ranges. The graphic on the right is from a study led by the Washington State Department of Natural Resources, in which they characterize long-term changes in Mesoscale kelp beds, so the bull kelp beds, within the South Puget Sound. Although the authors found floating kelp on the outer coast to be relatively stable and resistant to change, kelp within the Puget Sound haven't been so lucky. The graphic on the right depicts the subbasins within the Puget Sound and the last time they have witnessed 1 kilometer segments of bull kelp beds, so the type that you would recognize and think of as a forest. While both the west and the east basins have seen a high number of population segments since 1960, a good portion of the central subbasin hasn't seen bull kelp in nearly 60 years. On average, the authors found a 63% loss in linear extent within the entire South Puget Sound study region from 1878 to 2017, a number which goes up to nearly 96% in distinct subregions. The source of these declines aren't well known. While other parts of the world can point to overgrazing or other clear causes of loss, the issue is much more nuanced in Washington. Washington's Puget Sound Kelp Conservation and Recovery Plan, pictured here on the left, which was convened by the Northwest Straits Commission in partnership with a number of different regulators, tribes, and organizations in the area, identified key stressors that may be leading to the decline of kelp forests within the Puget Sound. I say may and might and maybe because we're not sure This is ongoing research, something that we're continuing to try to study, figure out, put in place, and help kelp recovery long-term. Some of those stressors I listed here. The first one, changes in water quality, describes a sensitivity to insufficient nutrients, like a lack of nitrogen available in the water column. It can also describe the warming temperatures outside of kelp's preferred range, which is thus 5 to 15 degrees Celsius, which is due to climate change. Just like water quality, biological stressors are equally varied. They could be attributed to herbivory from micro and macro grazers due to uncontrolled grazing, which is the situation of giant kelp in California, which leads to those urchin barrens. Other biological stressors may be competition or displacement by non-native species like sargassum. Finally, anthropogenic influences are the way human activity might contribute to kelp decline. Washington waters contain many fisheries, where commercially valuable fish are drawn out of the water through different means. These trawling and fishing practices have unknown and understudied impacts on kelp population distributions. Other anthropogenic influences include the effects of coastal development, like dredging and construction, that can change sedimentation or the turbidity of kelp ecosystems. Now that we've established the significant role kelp plays in Washington nearshore ecosystems and recognize that these valuable habitats are in decline due to stressors affecting them, we can begin to discuss what is being done and what can be done to protect kelp. I work for one organization that works in kelp restoration in the Puget Sound, aptly named the Puget Sound Restoration Fund. Our broad goals are to work through a diversity of programs and projects to restore important species in the region to promote healthier marine ecosystems. We have a number of different programs, from the aforementioned pinto abalone to Olympia oysters, as well as bull kelp. The latter two, Olympia oysters and bull kelp, which makes up our habitat program. Through our bull kelp restoration program, our mission is to reestablish historic beds because of their value and importance to healthy habitats for all the functions that we talked about before. PSRF is doing a number of different things to explore and advance bull kelp restoration in the southern Salish Sea. Among them, 3 of our primary approaches are listed here. On the left is displayed our enhancement site at Jefferson Point, or Dokagwas in Suquamish. Here we outplant juvenile bull kelp sporophytes to learn more about how to grow up healthy, self-sustaining kelp forests and explore the effects density and different environmental conditions have on their health and success. We work with tribes on outplanting kelp in their waters as well, growing up sugar kelp and bull kelp sporophytes as is requested. Moving right, pictured is Brian Allen with one of our collaborators from the Alberta lab in the other UW, University of Wisconsin in Milwaukee. She came out to aid us recently in developing our kelp lab, which is a space in which we are cultivating kelp from its gametophyte stage, both to preserve genetic populations in forms similar to terrestrial seed banks, as well as to grow up our own distinct kelp populations for our enhancement site. Our collaborators at the University of Wisconsin have been maintaining a collection of kelp genetic material from the Puget Sound and Strait of Juan de Fuca, and are now equipped to guide us in being able to do so in state. Finally, far right, are shown 4 of our so far established index sites, where we'll be deploying monitoring stations with environmental sensors to log the conditions that well-established kelp beds are growing in. Through the establishment of these index sites, we hope to better understand the conditions kelp are growing in and how they change over time and seasons. With the goal of establishing another 10 index sites to extend our range of monitoring, we hope to be able to compare different regions of the Sound and Strait to get a better sense of what changes are happening that might be leading to those kelp forest declines. I'm not just here to tell you all about the good work Puget Sound Restoration Fund is doing for bull kelp recovery. There are a myriad of ways that you listening along can get involved with kelp restoration yourself. The first group I'm covering are for the intrepid folks at home, those who like to get out on the water and hands-on directly. Both organizations listed here coordinate volunteers with specific skills or access to conduct surveys that contribute to the restoration efforts conducted by PSRF and other partners across the state. First on the left is Reef Check, which is a nonprofit international organization leading citizen scientists through established kelp forest survey protocols in our own state. We have worked with Reef Check over the past year to develop these protocols parallel to our own to standardize our methods. Reef Check trains interested and experienced divers in conducting surveys and then leads dives at sites throughout the Puget Sound and Strait of Juan de Fuca. They have trainings once a year, usually in the spring, and are expecting to have one early 2023. If you're interested, I really recommend checking out their website to learn more and stay tuned. Those who have kayaks can contribute to the Shoreline Monitoring Toolbox and Database, a resource which is assembled and handled by the Washington Sea Grant and University of Washington. This database contains a number of standardized protocols for community science groups to use and contribute to shoreline monitoring. For bull kelp, the toolbox uses kayak-based survey protocols developed by the Northwest Straits Initiative, listed there. Another way to get involved is to join citizen science or community science organizations. Citizen science describes the efforts of members of the general public to contribute to scientific pursuits across disciplines like biology, chemistry, physics, and so many more. Citizen science organizations are a great place to turn when you want to get involved, but aren't sure where or how to get started. These organizations are formed to guide volunteer scientists through established projects or initiatives to centralize effort and gather like-minded marine science enthusiasts. Here, I listed two groups from your own neighborhood. The first, Resources, is you might have heard of it, nonprofit organization with a simple goal of protecting the environment of the Central Salish Sea. From marine ecosystems to climate actions to fighting for sustainable, just, thriving communities and schools, they mobilize efforts across so many different projects. They have 4 initiatives which are specifically surrounding protecting the Salish Sea that I just checked out. One focuses on orca recovery, which connects across their other projects like preventing oil spills from harming marine environments, and engaging politically with the governor's Orca Recovery Task Force. Another initiative is the North Sound Baykeeper team, which is involved with community science, which is a more involved community science group who, under the leadership of Eleanor, who's here, conducts monitoring surveys and beach cleanups to draw people into that baykeeping effort. The last one I want to mention, which seems relevant, is the involvement with Aquatic Reserves, Cherry Point and Fidalgo Bay. They convene a citizen stewardship committee and invite folks interested to get involved, whether by sitting in on committee meetings or visiting and becoming familiar with the Aquatic Reserve. Whatcom County Marine Resource Committee is a similar resource available to those of you who are joining and live in Whatcom County. This voluntary citizen advisory group counsels the county council on marine resource subjects and projects of concern. Much like Resources, they have a handful of projects, inviting folks from different backgrounds and experiences to get involved in whatever way they want or feel capable. For the kelp concerned at home, they have a bull kelp project and a well-detailed webpage, which includes what survey protocols they use and what local sites they survey. Much like the Shoreline Monitoring Toolbox and Database, they use kayak-based protocols to conduct their research. More information on both these organizations and how to get involved can be found on their websites. I really recommend go checking them out. Next, this graphic, created by PSRF's Executive Director, Betsy Peabody, includes a breadth of different actions people can do to support kelp, no matter who they are or what they do for a living. Actions are broken down as those possible by folks who live adjacent to the sound, what can be done within your community, what can be done while you're at work, what can be done into the day-to-day, and what can be done when you're on or in the water. There are so many ideas here that there's likely something that appeals to you or your lifestyle. There's some that I want to linger on and talk about a little here, because I recognize that this text is very small. But if you're interested in this graphic, please reach out to me, or when this presentation becomes available after the fact, I really suggest coming back, pausing, and giving it a good read through. For the educators in the crowd, folks who work with students across ages on any number of topics, adding kelp to your curriculum is one simple change you can make. Engaging students on kelp topics, from the history of kelp in Washington to the ecological functions served by kelp forests, can generate that curiosity in different generations. If you live along a shoreline and own property, you can manage runoff from your property to reduce the nutrient loading in the water. Like the Conservation and Recovery Plan mentioned, kelp can be sensitive to changes in nutrient availability, especially either the insufficiency or the excess of nitrogen. Nitrogen is a common component in most fertilizers, so making sure you're monitoring your runoff and reducing the amount of nutrients that you put into the shoreline can benefit kelp long-term. For the climate activists, or the folks who might actively advocate for climate change policy and action in their local and federal governments, the connections to kelp are more intuitive than you may think. One stressor that kelp is notably sensitive to is rising sea temperatures. As a cold water organism, temperatures outside of that preferred range inhibits growth of healthy kelp beds. Including rising sea temperature within your action and advocacy keeps you kelp-minded in your already proactive efforts. Finally, anyone who has the means to make green financial decisions should investigate how to support the growth of a domestic kelp market. A lot of commercial ventures are putting kelp products out there, and everything from toiletries to snacks to sneakers. Supporting kelp products stimulates that industry, which can lead to more kelp being put into the water long-term. Regardless of who you are or what you have to offer, one of the best things you can do for kelp in Washington is continue to learn and stay informed. There are so many resources available online, with many videos, articles, and stories always just a click away. Organizations within Washington are a great place to start, as the Department of Natural Resources, Nearshore Habitat Team, and Puget Sound Restoration Fund both have an abundance of information on kelp available on their sites. One resource I really love to promote, are linked here, are story maps, which walk you through research in very straightforward ways. For folks at home who have smartphones, I've attached 3 story maps from DNR and PSRF that tell 3 different stories about kelp, including photos, maps, and graphics, taking you around the Puget Sound to experience kelp forests and their loss in the region. From the previously discussed article characterizing the loss of kelp in the South Puget Sound, to a story map developed by PSRF telling the tale of the kelp expedition last summer, these story maps serve as a starting point to ignite curiosity on all things kelp. For the folks without the technology to scan QR codes, I also included details below each code, which you can Google and get the link to this ArcGIS. If you find anything here interesting, sharing it with people in your life and engaging them in conversations about kelp forests in Washington passes on the message of these important habitats and taking a stand to protect kelp. To wrap up, I want to quote Carrie Ann Monahan, who is an educator, biologist, and citizen scientist advocate. In a TED Talk, she defined and described citizen science as a means of bringing people into the fold of science, from their couches, desks, and own backyards. There are truly so many options for contributing to science, among the ones I have listed, and the ideas that might be forming in your own heads. In her talk, she finished with what I felt was an especially strong idea. In your mind, I want you to create an image of a scientist whose work has changed the world for good. I have a picture in my mind, and it's abundantly clear to me. That picture looks exactly like you. You're the next round of scientists. The future of kelp is in my hands, but it's in yours too. So let's work together to protect and restore kelp for many, many generations to come. Like I mentioned when I started this presentation, all of the work I've spoken to you all about here was possible due to the tireless effort of the rest of the Habitat team, PSRF. From left to right is Brian Allen, our Director of Restoration, Hillary Hayford, our Director of Research, and Gray McKenna, the Kelp and Oyster Program Specialist. On the far right is Kathy Burnham, our dive technician from this past summer and dutiful photographer of all things kelp. Every photo that's uncredited in this presentation was one she took in the water during our surveys. Of course, none of the work we do would be possible without our partners. I've listed some here, but there's an impossibly long list of people who have helped in some small way. Not listed here are the folks listening who have may have already taken that first step to get involved. As constituents, as consumers, as recreational watergoers, as so much more, the work we do with all of our partners includes the efforts you all make to support us. Kelp recovery will take a village, but if we all do something, we can all do great things. Finally, here are some of the research articles I cited. If anyone's curious about these, I'm more than happy to share them with folks. Thank you for listening, and I'm really excited to answer any questions.
Thanks so much, Jessi. That was a great presentation. And I will definitely be thinking next time I'm out doing one of those kelp surveys, kayaking around, about how I'm breathing in the oxygen that the kelp has recently produced. So that's a wonderful thing to think about. So we have a number of questions, starting off with Lyle asking about, are there any negative ecological impacts due to kelp farming?
No, not so. There's a great regulation process that goes into commercial ventures for kelp to prevent like any negative ecological impacts. The species that are used and put out into the water are regulated by DNR and NOAA to make sure that they're not impacting local kelp beds. But one of the questions that we're investigating right now is what is the impact of different genetic populations on each other, specifically looking at the straight versus the sound species to see if there's any notable difference. So whether or not commercial ventures have any impact on that, we don't really know, but it's definitely a question we're asking.
Great. What about recreational harvest?
Not really. For bull kelp, for canopy kelps in particular, not a lot of people harvest it recreationally. Even among the Coast Salish tribes in the area, it's not often used for food. It's sometimes used, like I mentioned, for creating tools and vessels. Most of the harvesting that is done is regulated. It's within the shellfish collection permit. And it hasn't ever been significant enough for it to be individually regulated. So it's not such a big take.
Great, thanks. The next question is, will the green crab invasion infect kelp populations?
That's an interesting question. I don't know a lot about green crabs. I'm thinking specifically, I don't know their foraging habits. I'm under the impression that they're a near shore, usually intertidal species. So whether or not they can access kelp forests is definitely a question. I imagine if they are a facultative forager, so if they can eat kelp in plants, they might be a problem, but I don't know enough to say.
My understanding with green crab is that they really like the muddy areas, which might not be where kelp is found, but eventually they might take over a lot more of the shoreline and get less picky about their habitat. So it'll be interesting to see
definitely
down the line. And another question is, how do you attach outplanted kelp to holdfasts?
Yeah, so what we do actually, so in our kelp lab, we raise up the sporophytes from a microscopic stage. And what we do is we actually seed them on spools of threaded twine. So we'll keep the sporophytes in a container with the spools so that the only substrate they can attach to is that spool. And then when it comes time for outplant, they're already seated on the line. So all we have to do is unwound that line around concrete anchors, which are usually pyramids that we have specially made, so that they're already on that twine and they grow up. In that one picture that I can go back to briefly, you can actually see that they're growing directly on a line there. So that's why they're all like that.
Neat. Just a reminder, if people have any more questions, feel free to type them in the Q&A or chat box. Another question that we had, I am sorry, I'm going to mispronounce this word, are laminariales decreasing in other regions?
Yeah, I can speak specifically for bull kelp because, or for canopy kelps, because those are the ones that I'm most familiar with. There is a big concern for them across the west coast of America and up through Canada too, because they are being overgrazed in some regions by urchins. If you're familiar with the concept of urchin barrens, it's the uncontrolled grazing of urchins on the kelp that almost completely demolishes kelp populations and they can't bounce back. There is in Washington, it's not the same problem, like I mentioned, so it's more nuanced here, but definitely around this area, it's a big concern. I'm not super certain internationally, but I do know there are a lot of restoration practitioners across the globe working in different kelps, so I'm sure there's concerns everywhere.
Yes, I'm really happy that kelp is getting all of this much needed attention. It's really great. I have a question about maybe a little bit more specifically about Cherry Point. So the Whatcom Marine Resources Committee surveys at Cherry Point, and I know DNR also surveys at Cherry Point and has been off and on over the past several years. And you mentioned that temperature was one of the driving factors, and it seems like there's some data to support that sort of driven some of the kelp populations growth or retractions over the years. But one thing that there's been some just speculation. There's really no data that I know of to really support it, but I'm wondering from your experiences, how big of an impact does sediment have in it? Because at Cherry Point, there's feeder bluffs there. And so periodically there's these landslides. And so a whole bunch of finer sediment goes out into the environment. And it seems like there's sort of areas where there's eelgrass growing and there's kelp growing around the eelgrass. And I bet that has something to do with sediment. But I'm just kind of curious how, because some years it seems like there's shrinking kelp beds in some areas. And I sort of wonder if some of that has to do with maybe the sediment that's on the bottom that's moving around.
Yes, absolutely. I don't know necessarily how big of a role it has versus some of the other stressors, but sedimentation is a big concern. Kelp is pretty picky about what it settles on, especially considering that the holdfast needs something to attach to. They usually prefer gravelly surfaces or cobble of various sizes. And that is the easiest for those holdfasts to attach to and support that giant kelp and bull kelp structure. If they don't have that strong of surface to attach to, they might not be able to grow up to maturity, because if that sediment, it continues to move and unsettle, they can't hold in one place and won't be able to grow up. So yeah, it's definitely one of the many stressors contributing to their decline.
Great. Thank you.
Yeah.
Well, I am not seeing any other questions. Thanks so much. You answered a lot of the questions I had during your presentation. So
Great.
That was great. Thank you so much for sharing your knowledge and brain power with us today. And folks can reach out if they have more questions. And so with that, we'll move on to the last but not least presenter of the day, Lillian, and Hannah will introduce her, and yeah, go for it.
All right, for our last presentation, we have Dr. Lillian Aoki. She is a research scientist at the Data Science Initiative at University of Oregon. She studies coastal ecosystem dynamics across space and time, working to understand how climate change and other stressors impact ecosystem resilience. A native of Virginia, she studied seagrass restoration at the Chesapeake Bay area before moving to the Pacific Northwest in 2018 to study seagrass disease. Her current work focuses on the benefits of seagrass restoration and conservation in Oregon, and she will be presenting on stressed out seagrass.
Thanks, Hannah. That was a great introduction. And thanks, Eleanor, and everyone at Cherry Point for putting this on. This has been a great set of talks today, and I'm really excited to bring seagrass into the discussion. I'm sharing my screen, so hopefully folks can see this presentation. Sorry, let me just get the Zoom set up. Okay, so so my name is Lillian Aoki. I'm a researcher at University of Oregon. I'm going to be sharing some work that I participated in, mainly working out of Friday Harbor Labs in Washington, which is where I did my postdoc. And this is a very collaborative and team effort, and I just want to emphasize that at the beginning. I'm going to be sharing a ton of data that's been collected over the last decade, and clearly I did not do all this myself. So I just want to start with that acknowledgement. Thinking about seagrass ecosystems, I'm guessing that many folks on this call are familiar with seagrass, but just to give everyone a refresher, and for anyone who's maybe not that familiar, I'm going to start with kind of the global context for seagrass habitats, thinking about what these habitats are, why they're so important, and what are some of the stressors that they're facing. The main part of the talk, I'll be focusing in on eelgrass vulnerability in the Salish Sea, and specifically in the San Juan Islands. And then for the end of the talk, I'm going to take another step back out again and think about putting that Salish Sea story in a broader context and thinking about patterns in eelgrass dynamics up and down the west coast of North America. So definitely, again, if there are questions, please feel free to put them in the chat, or even if something's confusing throughout, I'd like to know that and be able to provide clarification. Okay. So seagrass meadows, we just heard a ton about kelp, which are another amazing nearshore ecosystem. And I want to sort of celebrate these amazing nearshore ecosystems that maybe aren't as well known as some others. And so seagrasses are another kind of maybe underappreciated habitat out there in the coastal ocean. And so seagrasses are found in coastal waters of every continent except Antarctica. Here in the Pacific Northwest, we have mainly eelgrass meadows. So Zostera marina is the dominant species, and we mainly see these intertidal meadows. So the seagrass is actually exposed at the low tides. The plants will come out of the water. But in many other areas where there are other species, and there's seagrass that is entirely subtidal, it can be found down to depths of 90 meters if the water is clear enough and there's enough light coming down for the plants to grow. A fun fact about seagrass is that it reproduces both sexually and asexually. So it can produce flowers, they have pollen, they can be pollinated, they produce seeds, they can create seedlings, but it also reproduces through clonal growth. So you can have the same genetic organism that's spreading, sending out rhizomes, sending out rameates and new shoots, and just spreading and spreading. And this means that some of the oldest and largest organisms on Earth are actually seagrasses. So there's a clone in the Mediterranean that's been identified as having persisted. The same genetic organism has persisted at least 80,000 years, and it's currently over 15 kilometers in size. So that's, I think, pretty incredible, and another reason to appreciate these amazing ecosystems. Seagrasses, like kelps, which we just heard about, are foundation species. So they actually create the physical habitat that other organisms can use as their home and as their habitat. And this includes many commercially important species, many culturally important species. It means that seagrasses are strong hotspots of biodiversity. And it also includes many species we might not think about. So all these little tiny critters that are living right there on the seagrass leaves, it's also habitat for those guys. Seagrasses are also ecosystem engineers. And so what this means is that they modified the habitat and actually improve the environmental conditions for their own benefit. And so for seagrasses, the way this manifests is that they actually will slow down the wave energy. So the currents that are moving through a seagrass canopy, a stronger current can be weakened. And this leads to the deposition of particulates. So anything that's suspended in the water column can be settled out in the seagrass meadow. And for the seagrass, that's a benefit because it means the water becomes more clear, it increases the water clarity, and so more light can penetrate. The seagrass are able to grow from that and photosynthesize. But it also means that seagrass sediments will accumulate over time. So the bed will actually accrete and the sediments will raise up over time. And this is really important for us from a human perspective, because organic matter and carbon can be stored in those sediments. And so we can think about seagrass meadows along with tidal marshes and mangroves as being one of these blue carbon ecosystems where carbon is actually being sequestered in those sediments, it's being held there, it's not returning to the atmosphere. And this actually has the potential to be an important factor in mitigating carbon dioxide emissions. So there's been a huge amount of scientific interest over the last decade or so in understanding what really is the sort of blue carbon potential of seagrass meadows. Can they really contribute? Can they be a natural climate solution, right? And so this has motivated restoration and conservation, a lot of interest, not just from scientists, but from NGOs and from governments and from others who are interested in understanding this role that seagrasses might be able to play for us. Okay, so seagrasses do amazing things. They sequester carbon, they support biodiversity. Unfortunately, we are losing a lot of seagrass meadow area. And so this is a figure that comes from a review paper that just looked at different studies of seagrass and different areas that have been increasing or decreasing. And so in the symbols, you can see the size of the symbol relates to the number of studies, and then the color of the symbol shows whether the area is increasing or decreasing. And so bigger symbols with more red means we're losing seagrass. And unfortunately, that's what we see in a lot of the world. Now, obviously, there are a ton of data gaps, but this is overall the trend is that seagrasses are really in trouble in a lot of places. There are a lot of reasons for that. So physical disturbance is one stressor that seagrasses face. So this is an image of a meadow. I think it's in Portugal. But you can see this is actually showing the effects of boat anchoring. And so each of these little light colored patches in this seagrass meadow was initiated from a boat anchoring that caused physical disturbance. And then it can, the boat can actually rip up seagrass plants, but then there can be scour, and those things combined can cause more disturbance to the meadow. Another stressor is nutrient runoff. So we heard a little bit about this in the Kelp talk, but nutrient runoff can be really damaging to seagrass meadows. These nutrients coming from fertilizer or from urban sources or from wastewater, all of these things combined can cause an algae bloom to form, and then that algae can smother the seagrasses. And then there's also wasting disease. So I'll be talking more about wasting disease later in the talk, but this is another source of stress to seagrass ecosystems. And in the early 1930s, there was a massive outbreak of wasting disease, which actually led to the loss of meadows throughout the Atlantic basin. So this is another potential source for seagrass decline. Of course, seagrasses are also very vulnerable to temperature stress. And this is becoming increasingly important as we see oceans warming under climate change. And so, just like on land where we have heat waves, we have extreme, unexpected or unusual temperatures, seagrasses in the ocean can also experience marine heat waves. And of course, they're rooted, they don't have anywhere to go to escape those extreme temperatures. And so they really can get cooked when these marine heat waves happen. This is a figure from a study in Australia. They had a massive marine heat wave several years ago. And this basically shows a strong correlation where as the marine heat wave persisted, so the longer the marine heat wave lasted and the more intense these extreme temperatures were, the seagrass shoot densities just declined pretty rapidly. And so there's definitely a major stress from temperature for these seagrasses. Okay, so the best evidence we have right now suggests that seagrass losses, not only are we losing seagrasses, but it seems that losses are accelerating. So based on our historical data, it seems that we're seeing more loss of seagrasses in recent decades compared to what we think might have happened earlier in the 20th century or earlier. Unfortunately, we don't actually have great data. So this is a figure from that Whatcom paper, which I mentioned earlier, is a review that it's sort of the best we have, but we don't have a ton of recent data. And part of that is that we actually just don't have great information, especially globally. There's a lot of missing data in terms of where seagrasses are, what are the trends that they're experiencing. But luckily, we are starting to see new tools and technologies that are coming online and are giving us the opportunity to improve those inventories and to improve those data sources. So this is a set of images looking at an area of coastline using different remote sensing technology. So a drone here on the left-hand side, this is a very high resolution, 4 centimeter resolution of this image, all the way over to a Landsat satellite. This gives you a 30-meter pixel resolution. So it's not quite as great resolution, but there's a really long temporal. We have 30 years of Landsat data. So all these different technologies are starting to give us sort of new information and new tools and really helping to improve our seagrass data so that we have a better understanding of what really is going on out there. Okay, so if I need to summarize what's happening, the global context for seagrass habitats, just a few points, I would say, seagrasses provide critical benefits. They're really important ecosystems. Unfortunately, we are seeing declines in many regions. And at the same time, we're seeing this increasing interest in seagrass conservation. And so we're seeing a big surge in studies of seagrass and in the kinds of data that we need to understand how to restore and conserve these habitats. Okay, so I'm gonna move to the second part of the talk, which is focusing, zooming in onto the Salish Sea and the San Juan Islands, and thinking specifically about warming temperatures and wasting disease as these two stressors. So not to sort of repeat myself too much, but just to reestablish, here in Washington State, in the Pacific Northwest, eelgrass is a particularly important habitat. It's been designated as critical habitat by the Washington State Legislature. Similarly to kelp, seagrasses provide this foundation of the food chain. So we have, for example, herring can spawn on eelgrass leaves as well. Meadows can provide habitat for juvenile salmon and other important fishes. And of course, all of that travels up the food chain and supports our charismatic megafauna, such as orcas, right? So these are very culturally important and economically important species here in this region. And eelgrass really is one of the foundations of all of those interconnected ecosystems. Okay, so in the San Juan Islands, we've been monitoring seagrass for about a decade. This is work that's been done through Dr. Drew Harvell's lab at Friday Harbor Labs. And so this is one of our monitoring records. So this is a plot of seagrass shoot densities here on the y-axis, and then just the year from 2013 to 2021. And each of these colors indicates a different site. And what you can see overall is that we've had major declines. So seagrass shoot densities have declined by about 90% over this time period. And this is kind of concerning, right? This is pretty concerning. And this is, again, this is focused on intertidal eelgrass. I'll just say that. So this is not necessarily the same thing that's happening in the subtidal. But we are seeing these major declines of intertidal eelgrass. The San Juan Islands have been designated as a region of concern by the Washington DNR, which does more widespread monitoring in other places in Puget Sound. And the San Juan Islands really stand out for their seagrass declines. Something that we've noticed from our monitoring records is that these declines may be associated with the marine heat wave. So folks on this call probably remember the blob. So this huge, the largest and longest, I think, marine heat wave on record in the Northeastern Pacific. This was a period of about 2 years, 2014 to 2016. We had unusually warm temperatures. And that's the period when we started to see this sort of sustained decline in seagrass densities. And there really has not been recovery since 2016 of those declines. And so we really do think that warming is stressing these seagrasses, is driving a lot of these declines in the intertidal. Of course, these extreme heating events just keep happening, right? So again, people on this call, I'm sure, remember and probably experienced another extreme event in June of 2021, the Pacific Northwest Heat Dome, as it was called. This was not a marine heat wave, it was an atmospheric event, but it was extremely warm. This map is showing us the air temperature anomalies. This is data from NASA. And of course, the Salish Sea, all of the San Juan Island eelgrass, right in the middle of that extreme temperature anomaly. To give you a sense of what the intertidal eelgrass is experiencing at those times, this is some temperature data from loggers that we had deployed in the intertidal during this event. And this is a kind of busy figure, so I'll walk you through it. Each panel is a different year. So we have 2019, 2020, and 2021. We had temperature loggers in the lower intertidal, so closer to the ocean, and also in the upper intertidal, so closer to the shore. And then again, each of the colors is just a different location. And in the graphs, I have a dashed line at 25 degrees Celsius. And you can see that in 2019 and 2020, we never had temperatures that crossed that line. But then at the end of June in 2021, so during this really extreme heating event, we had temperatures almost as high as 35 degrees Celsius in the intertidal. So that's just really extreme. Like it's really, really hot. It's way beyond what these plants are adapted to and what they are, expecting to experience in this region. So in addition to our shoot counts, our surveys where we go out and count shoot densities, we also have started doing mapping with drones. And here I want to shout out Dr. Bo Yang at San Jose State University, who's our lead collaborator on the drone work. And so Dr. Yang has been helping us map seagrass meadows in the San Juan Islands since 2019. And we were actually really lucky that the year of this 2021, the year of the heat dome, we actually mapped the meadows just following the heat dome about a week later. And so we're actually able to see, what was the effect of this extreme event on these meadows. And it wasn't great. So it's really cool data, but unfortunately, what the drone surveys were showing is a widespread decline. So again, each of these this is the same image. This is a time series of images. So we have 2019 through 2021. And each image shows the same area. And here the sea, the ocean is on this side, the land is on this side of the image. You can see this intertidal area where we have our transects, do our monitoring, and we've highlighted the seagrass area in green. So we've sort of pumped up that green color so you can see where the seagrass is. And it looks, pretty nice in 2019, pretty nice in 2020. In 2021, a lot of it is just gone. So that upper intertidal area is just bare sand now. It's not seagrass anymore. And what these drone images allow us to see is this kind of landscape scale change. So we're not just looking at a few quadrats that we put along a transect meter tape, but we're actually looking at what's happening at more of a landscape scale picture. And unfortunately, we're seeing the same story at a lot of our sites. So this is another site, 4th of July Beach on San Juan Island, again, 2019. And in this one, the image is flipped. So the land is on this side, the ocean's on the right side. But the same story, you have a lot of seagrass coverage in 2019 and 2020, it looks beautiful and thick. And then in 2021, we're just seeing bare sand. So there's really dramatic landscape scale changes that we think are associated with this heat wave. Okay, okay. So we think that warming is causing seagrass decline. Again, this is the same plot that I showed you before where these densities are decreasing over time. And I'm just showing you this image. It's not that surprising that these plants are really vulnerable to heat stress. They're exposed, they're out of the water during the middle of the day. They can get dried out and desiccated. They're really kind of vulnerable to that thermal stress. But the other thing that we've been monitoring over this same time period is disease. And so we've been looking at wasting disease as well. And I'll give you some more details on that in a second, but I just want to put these two plots next to each other. So this is, again, shoot density on the top plot and wasting disease prevalence on the bottom. So this is the percent of individual plants within a given meadow that show signs of a wasting disease infection. And what we see is basically a mirror image. So earlier in the time series, wasting disease, infection rates weren't that high at most of our sites. But then when we hit about that 2016 period, following this marine heat wave, we started to see pretty high levels of infection at pretty much all of the sites. And that's persisted over time. So, we have these low densities that have persisted and at the same time, potentially higher rates of disease. And so the question is wasting disease also increasing? So warming seems to be stressing the grass and causing them to decline. Is it also increasing the disease? That's kind of a major question for us. Okay, so I'm going to step back now and kind of give you a little bit of a intro to wasting disease, if it's not something that you're super familiar with, which probably not everyone is a wasting disease fanatic. So seagrass wasting disease or eelgrass wasting disease is caused by a protist, Labyrinthulus austeri. So it's a very tiny marine organism that you can see here in a stained picture. And this organism will just enter the eelgrass tissue and it causes the formation of these lesions. So these areas of very dark black or this dark brown, this is tissue damage caused by the disease, and it keeps the plant from photosynthesizing. And so this damage can spread. It can actually kill off the whole leaf or a whole plant. And it has been implicated in these historic outbreaks. So I think I mentioned earlier that in the 1930s, there was a big outbreak of wasting disease in the Atlantic Ocean. And there were losses of meadows in Europe and in the US coast, East Coast, that were attributed to wasting disease. So although we have known about this disease for a long time, and there have been a number of studies, there's actually a lot that we still don't understand. And so some of the work that we've done here in the San Juans has been to address this question: how does wasting disease affect eelgrass growth? So what's really going on when these plants are infected? And then secondly, our second question that we want to address is, does warming make disease worse, right? So this idea that these higher temperatures that are stressing the plants, are they also increasing disease? So that first question, we want to understand the relationship between wasting disease and growth. And to answer that, we actually went out and did some tagging of some shoot marking in the field. And this is kind of a fun method where what we do is we go into the field and we actually use a little needle to make a scar at the base of an individual eelgrass plant. And then we leave that plant alone and we let it grow for a few days or longer, maybe a week. And the plant will continue to produce new leaves. It will continue, those leaves will continue to grow. And that scar at the base of the plant will start to move up the shoot. And you can actually see how much growth there's been between when you mark the plant and when you come back to harvest it a few days later. And so we do this shoot marking so that we can compare growth rates between diseased plants and healthy plants. And when we did that, these are some of our results from that study. So this is a plot showing you leaf growth rates on the y-axis and then the age of the leaf on the x-axis. So this is going from our youngest leaves. This is the freshest, greenest, newest tissue, and they grow really fast compared to the older tissue. And then we have the second oldest down to our oldest leaves, which basically aren't growing at all. They're pretty much ready to just fall off the plant and decay. So they're really not growing much at all. But for each of these categories, each of these ages of leaves, we compared the growth rates of healthy leaves and diseased leaves. And we found consistently that those healthy leaves are growing faster. So these blue points are a little bit higher, and it's hard to see because this is a log scale, so it's an exponential scale here. But the healthy plants are always growing faster than those diseased plants. So the infection is actually really inhibiting the plant's ability to grow. Infections also have consequences for the below ground biomass. So we think about the roots and the rhizomes of the eelgrass. That's where they're storing their carbohydrates. And so as the plants are growing all summer, they're building up sugar reserves in their below ground biomass. And then they use those sugars if there's disturbance. For example, if there's a winter storm, or just in the winter when the above ground biomass has died back and the plant needs to regrow in the spring, it uses those carbohydrates that are stored below ground to fuel that growth. And so what we found is that if we look at the sugar content of plants that have wasting disease infections, and we look at the severity of the infection, so this is how much of the plant of those leaves is covered by wasting disease lesions. So basically how bad is the infection? And as that severity increases, we see a decrease in the amount of sugar that's held in the below ground rhizomes. So there's less and less carbon being stored, there's less and less sugar being stored by the plant, and so the plant has less fuel to regrow after any kind of disturbance. So again, the disease is really impacting these plants both above and below ground. And unfortunately, this introduces the possibility of kind of a reinforcing cycle. So we have these two stressors. We have, our warming ocean temperatures, they're causing seagrasses to decline. At the same time, we have these disease outbreaks. They're reducing the sugar and reducing the growth of the plants. And that means that the plants are going to be slower to recover from any kind of disturbance. They're growing more slowly. They don't have as much sugar. They don't have as much fuel. And so they have a slower recovery, and that's probably going to make them more vulnerable to disturbance from things like heat waves. And so we kind of have this reinforcing cycle where these plants just are becoming more and more vulnerable to these different disturbances because they're both receiving both of these stressors at the same time. Okay, So this question, how does wasting disease affect eelgrass growth? We think we have some pretty good answers. Again, this idea that the plants are, the disease is reducing plant growth, it's reducing sugar stores, and it's making seagrass more vulnerable to disturbance. The second question that we were interested in, does warming make wasting disease worse? That still didn't, from this study, we didn't really have an answer. And so again, we have this idea that infections in the San Juan Islands seem to pick up after a marine heat wave. But to really answer this question, we actually needed to take a step back and bring in a broader geographic gradient and understand what's happening with warming and disease beyond the San Juan Islands. So this is where I'm going to start talking about West Coast wide patterns. And again, here, this is just a sort of angled view to give you a sort of continuous view of the West Coast of North America here. Eelgrass is found all the way from Alaska down to Southern California. Even Baja California has eelgrass. And so this eelgrass, it's the same species, it's Zostera marina, but it's adapted to very different growing conditions. If you think about the climate of Southern California and the climate of Puget Sound versus Southeast Alaska, very different climates, and the grass is adapted to these different conditions. And so in order to understand what the effects of warming are going to be, we wanted to look at this geographic gradient of the whole species. So it's growing across this wide temperature gradient. We wanted to understand what's happening. How are warming and disease going to interact across that gradient? Oh yeah, and so our question, what is the impact of wasting disease in a warming ocean across this geographic gradient? So that was kind of our goal with this bigger study. Okay, so for this West Coast wide study of wasting disease, this was really, really fun and a huge team effort. So we have field teams collaborating on this up and down the coast. So we have a team up in Alaska, we have a team in British Columbia, the San Juan Island team, folks in Oregon, and then folks in Bodega Bay and down in San Diego. So we have this whole geographic gradient. We had 32 different meadows that were being studied, and we implemented the same methods everywhere so that we could collect the same data and compare it everywhere. So we did these coordinated field surveys for 3 years where we collected all of the same information about the seagrass and about the disease. Again, we did these drone surveys, which I mentioned earlier, and we collected sea surface temperatures from satellites. So we used remote sensing data to get that comparable temperature metrics up and down the coast. A really fun and important part of this work is that we actually used artificial intelligence to measure disease. So because of the scale of this project, there were so many samples and so many sites, there's actually no way we could have done this study if we had to process everything by hand. So it just would have been a labor bottleneck. We just wouldn't have been able to do it. But luckily, we were able to collaborate with some computer scientists who helped us to build ELISA, which is the eelgrass lesion image segmentation application. And this is an AI program that basically speeds up our ability to identify disease and healthy eelgrass tissue. So during the surveys, we would collect eelgrass leaves, we would prepare an image such as you see here on the left, and then we run that image through ELISA and we get an output such as you see here on the right. So here, all of the disease tissue is highlighted in this pink color and the healthy tissue is highlighted in blue. And from this, we can calculate different metrics, right? We can understand the prevalence or the severity of the disease based on these metrics. We've trained ELISA on about 1,000 images, and through our testing, we have determined that ELISA is as good as a human expert at identifying disease on eelgrass tissue. So that means we're pretty confident about these results. And we've also done some testing looking for the pathogen DNA in these samples, so doing qPCR and looking for that pathogen DNA to confirm that, yeah, these samples that we are identifying as disease, that ELISA is identifying as disease, that we do see that Labi is present, Labyrinthula is present there, and that's the pathogen that causes the disease. So again, we're pretty confident about using these results, and we are really happy to use them because, again, ELISA is thousands of times faster than a person having to do all this identification by hand. Again, I want to mention these disease metrics. So we can look at disease prevalence, which is the presence or absence of disease. And we can also look at disease severity. So the severity is the percentage of that leaf that's covered by disease tissue. And that's based on calculating the lesion area itself. Okay, so I'm going to show you a bunch of data. And again, these are kind of dense figures, but I want to sort of, I'll walk through each figure and, I want to show you kind of get into the nitty gritty of this study because it's a very data rich study. So this is starting with some of our shoot density from the seagrass surveys. And again, so shoot density is on the y-axis here, year is on the x-axis, so the 3 years of our survey. Each panel is a different geographic region, and then each colored series in the panel is a specific seagrass meadow. And so the main thing, the first thing that you see looking at this is like, wow, there's a lot of variation. The densities were very different between our regions, and there's a lot of differences over time. But we do see declines in several of our regions. So if we look at British Columbia, if we look at Washington, Oregon a little bit, and certainly California in the Bodega Bay region, we do see overall trends of declines on seagrass density over time. And this is just 3 years. This is a pretty short time series, but it's not very encouraging to see those kinds of declines in that short period of time. Again, focusing on Washington, this is just the last 3 years of that longer time series I showed you before. But even in those 3 years, we see density declines of 45%. So again, Washington really does stand out as one of these sort of hot spots of seagrass decline. This is a plot of seagrass disease prevalence. And so this is similar to the last plot, but here we have disease prevalence on the y-axis. And so this is, again, the proportion of plants in a given meadow that are infected with the disease. And again, each region is its own panel, and each colored series is one meadow. And this is also, it's sort of a lot of variation. Kind of the takeaway from this is, there's variation in disease across time and space. And so we see high levels of disease in lots of regions, in lots of years, but there's not a consistent, increase or decrease at most of our sites. And part of the reason for this is that it's actually quite difficult to disentangle these changes in density and these changes in prevalence that are happening at the same time, right? So for example, in the Washington sites, the prevalence numbers have actually gone down over the last 3 years. The proportion of plants that are infected has decreased somewhat, but that's largely due to the fact that the plants have mostly died. So there's really not any plants there to be infected. So it's not exactly positive. We know these meadows aren't doing well, even though the disease prevalence maybe seems to be going down a little bit. So this is kind of a tricky plot to interpret. And the main takeaway is there's a lot of variation across time and space. So the piece of the analysis that really starts to bring these things together is when we start to look at temperature. And so again, our question here is, does temperature influence disease? And here we have our little cartoon of our pathogen related to our seagrass. And what we're trying to determine is, can we add temperature to this equation, right? Can we use some kind of temperature metric to better predict our disease dynamics? And we do this using what we are calling climate window analysis. And what I mean by that is that we have a temperature record over time, and we have some point in time when we do our sampling, right? We go out in the middle of the summer, we do our surveys, and we collect all of our disease data and our seagrass data. And it might be that the temperatures during that time, at the time of sampling, are really important to predicting or to understanding disease dynamics. But it might be that there's some climate window prior to the sampling that's actually more important and that's actually influencing our disease later in the summer. And that climate window could be a short period of time, it could be a longer period of time, and it might actually be distant in time from when the sampling occurs. So it might be that the spring temperatures, for example, or the early growing season temperatures are actually more important for what's happening in the midsummer when the disease and the seagrass are sort of at their peak. So with climate window analysis, we're basically systemically testing these different periods of time and these different temperature metrics to understand this potential relationship with disease. The other thing that's really important about our temperature analysis is that we're analyzing local temperature anomalies. So we're actually looking at the difference between the measured temperatures and what the long-term average is for a specific site. We're doing that again because our study covers this geographic gradient up and down the coast, and this means that the eelgrass meadows are experiencing very different actual temperatures. So this is the plot of sea surface temperature on the y-axis here across the 3 years of our study. And the different regions are in different colors. And these gray bars are just showing you the midsummer sampling point. So this is when we go out and do our surveys. And you can see that there's a lot of variation, right? Like San Diego in this yellow is really warm compared to all of our other sites. And so the winter temperatures in San Diego are warmer than a lot of the summer temperatures in some of our other regions. And so if we just looked at raw temperatures, you know, the temperature that's hot for a plant in Alaska isn't going to be hot for a plant in San Diego. And so to account for this kind of local adaptation, we want to look at the temperature anomalies. So we look at the differences compared to the long-term means in those locations. Okay, so when we start to put this together, this is what it looks like. So we have, again, sea surface temperature here on the y-axis. The x-axis here, this is the month of June, and this is for 2019. So this is the first year of this study. And this dashed line is that long-term local average temperature. And so this is what we would expect based on a decade of sea surface temperature measurements. This is the temperature we would expect to see at this location. And then the solid line shows you what that location actually experienced in 2019. And so when it's above that dashed line, we're seeing a positive anomaly, right? So it's warmer than usual. And below that is a negative anomaly. And so we can see at this particular site, most of the month of June, the anomaly was positive, right? The temperature was above normal, and this was a high disease site. In contrast, at our low disease sites, we tended to see that the actual temperatures that were experienced were typically below that long-term mean. So we typically had a negative anomaly at the low disease sites. And so if we do this analysis across all of our sites and we put it all together, what we end up with is a relationship between these positive anomalies and disease prevalence. So basically, sites that are warmer than average for that location tend to also have more disease. And this holds true across all of the regions. So this includes all of the sites up and down the coast. And what this means is that because eelgrass are adapted to their local temperatures, they're going to be vulnerable to warming, even if it's not as warm as the species can experience, right? So the absolute temperatures that are going to kill eelgrass, for example, you know, might not get that hot in Washington or in Alaska, but if it gets hotter than normal, it's still going to potentially increase the disease. Okay, I know this is a lot, a lot of data, a lot of plots. Just a couple more. The last sort of data point I want to make here is we did the same analysis looking at severity. So those other disease metrics, looking at the severity of the disease and the lesion area. And again, that's just a proportion. If we have looking at a single eelgrass leaf, you know, what proportion of it is damaged by the wasting of these lesions. And we see here when we do the analysis that there's a positive relationship between the disease severity and the temperature anomalies in May. So this is about 2 months prior to our summer sampling. So there's, again, those spring temperatures earlier in the growing season, those seem to have a strongest relationship with our summer measurements of disease. And so both severity and lesion area had that same positive relationship with these spring temperatures. And so again, we're sort of working to unpack what this really means. You know, it could be that warm temperatures in warm anomalies in the spring are affecting the way the eelgrass grows. They might also be affecting how the pathogen grows or how abundant the pathogen is. And so we're sort of still working to unpack what that mechanism might be, but we do seem to see this consistent relationship where it's the spring temperature anomalies are related to that summer disease level. Okay, so if I can pull together this West Coast wide study and kind of summarize the main points again, across this gradient of the West Coast, we do see the San Juan Islands sticking out as one of these hotspots for seagrass decline. Not the only place, but it's definitely a region that we think is experiencing a lot of decline and definitely experiencing a lot of stressors. We found that our disease metrics were correlated with climate warming. So the prevalence, the severity, and lesion area all had correlations with different warming metrics. And the key here is seasonality. So again, those spring temperatures may be really important to understanding what's happening during the summer, during sort of the midsummer peak biomass for the seagrass. Okay. I feel like I went through this really fast. So if there are questions, I will definitely clarify at the end. But yeah, so I kind of want to bring this back together and, sort of take a breath for a moment. A lot of what I've been talking about can be kind of oppressive. We're talking about seagrass, we're talking about how important these ecosystems are, and they're experiencing all these stressors, and there's disease and there's warming, and it can kind of be oppressive because it's not like there's something you or I can do right now to stop marine heat waves. That's not something that there's an action we can take at a local level to do something about that. But I think I kind of like to flip the script a little bit and think about this really as a moment of action, a moment of inspiration. I don't know if folks are familiar with the UN decades. These are basically sort of high-level calls to action, and there's a lot of organized there's sort of organized work being done around different themes. And so we're right now in the UN decade of ecosystem restoration. We're in the UN decade of ocean science for sustainable development. And so there's just this concerted push from really local to global levels to protect these ecosystems, seagrasses and other important coastal ecosystems, and to really both get the data we need to understand them, but also to take the actions we need to really protect them. And I just want to I like to end my talks on trying to get a kind of positive note out there. So I want people on this call to know seagrass restoration is possible and it can be successful. And so this is a figure from a recent review of marine restoration, not just seagrasses, but all kinds of marine ecosystems. And there's just been exponential growth in the last couple of decades of projects being implemented and restoration efforts being put out there. These pictures on the right are from a restoration effort that I was involved in the San Juan Islands a couple of years ago. DNR is doing restoration work throughout Puget Sound. And so there's really just incredible interest, again, in restoring and conserving these ecosystems. And I want to emphasize that restoration doesn't just mean planting plants, right? It doesn't just mean finding seeds, seagrass seeds, and planting them, or harvesting donor shoots and outplanting them. It can also mean things like improving water quality so that the seagrass that's there has a better chance of growing and becoming resilient. It can mean, protecting areas from disturbance from boat anchoring or from shading from coastal development like docks. And so, all of these actions that we can take on the local level, and we can bring our sort of efforts to bear, even if we can't, fix marine heat waves all by ourselves. I think there is a lot that can be done that can really give these ecosystems a chance to thrive and a chance to provide us with all of those amazing services that they do. So I'm gonna end there and give a shout out to all of the collaborators who worked on this, all of the funders, of course, everyone in the audience. Thank you for sticking with this. Many presentations and a lot of science being thrown around. And so I think there are probably some questions, and I'm happy to answer them.
Yes, thank you so much for that wonderful presentation. And yes, it's been a day packed full of science, which is wonderful. So we do have some questions, starting with Lyle's question from earlier. Does eelgrass have mycorrhizal or fungal associates like terrestrial plants do?
Yes, it does. I think, well, let me back up and say, I don't know as much about fungal associates. So I think that that's actually an area of research that's sort of picking up a little bit. There are definitely bacteria in the rhizosphere surrounding the roots that do things like fix nitrogen or have other functions that are really important to the plants. I think that often seagrass research tends to kind of lag terrestrial research. So there's been sort of things like seagrass microbiome research or this fungal research has kind of just started to take off and is a little bit behind some of the terrestrial ecosystems. But to our knowledge, yeah, there are a lot of those same associations are there.
Great. Another question was, is the wasting disease the same as the one with starfish?
No. So this is, probably like scientists should come up with some names for diseases besides wasting disease. I feel like every ecosystem has their own wasting, and it's a different disease. It's so wasting disease and starfish, they're actually still working to identify what's the causal organism, what's the pathogen that's causing that. And there's a lot of work being done on that right now. but this is a totally separate disease and a totally separate causal organism. And it's actually been identified. The Labyrinthula has been known since 1980 something, I think. I'm not going to remember off the top of my head, but it's been known for a long time. And sort of the presence of the pathogen has been known for a long time.
Great, thanks. The next question from Erica is, she first starts off with, thank you for your essential work with eelgrass. Do any of your monitoring sites have desalinization plants nearby? I wonder if you have considered salinity as an additional stressor, as the San Juans have little freshwater input compared to other places in the Salish Sea.
Yeah, that is an excellent question. So salinity is really interesting because especially when we're thinking about this sort of disease dynamic, because salinity, Zostra likes marine conditions. It likes to have high salinity and be close to or at sort of marine salinities. And it doesn't really do well if it gets a lot of fresh water. But it turns out that the pathogen also doesn't really like fresh water. And so there's sort of a weird tension of like whether in some places, Zostra can grow in more brackish or more fresh conditions, not actually fresh, but along the spectrum. And there's sort of a question of whether those can be kind of refuges for protection from the disease. And this is something that's definitely still being studied. I think that there's just not enough data to really make any conclusions at this point. But yeah, the salinity gradient is really important. And I think, it's interesting because the San Juans don't have big freshwater inputs, but they do, when you think about, for example, these tidal flats that are out of the water, and if you get a rain event while those flats are out, you can still get kind of freshwater pulses on a really micro scale. So anyway, this is stuff that's actively being researched, but I don't have a good answer except to say, yes, we need to think about salinity.
Great, thanks for that. Diane asked, do you have any idea what a really cold winter will do?
That is a great question. And no, we don't. Yeah, no, we don't have a great idea of what that will do. I think there's sort of multiple parts of the system can be affected by temperature. So both the grass and the pathogen can both respond to temperatures, right? And generally, I will say that it does seem like warmer winters seem to lead to higher seagrass shoot densities in the summer. So they seem to like those warmer winters a little bit better. But in terms of how that will affect the disease overall, no, I don't have an answer for that.
Thanks. And we have another question from Lyle, and I apologize for mispronouncing anything here. Is Labyrinthula Zostra always present in Zosta marina, and does it always produce some degree of lesions? Does it affect Zostra japonica? Does eelgrass there's a lot of questions here, so I can repeat any of it if you want. Does eelgrass decrease with high temperatures without the presence of the pathogen? Have you seen any wasting disease in Cherry Point or Birch Bay areas? Can a layperson differentiate between the wasting disease and other causes of damaged leaves?
Yeah, these are all great questions. So starting from the beginning, and if I miss something, let me know. But Zostra or Labyrinthula does tend to be present pretty much anywhere that you have Zostra. So it's not necessarily causing an outbreak everywhere, but if you go looking for it, you pretty much will find it anywhere that there's eelgrass. At least that's the case right now. And I think there's more and more interest from the seagrass community to understand, where is it causing an outbreak? Why isn't it causing an outbreak in some places where it might be present? I think there's a question about japonica, and I'm not sure about japonica. Zostra or Labyrinthula can infect other species. There have been some documented cases of that. I'm not sure about japonica if that's been tested or not. But it is a really widely distributed organism throughout sort of marine environments. In terms of heat stress, yes, heat stress will absolutely damage seagrass beds without any disease interaction. So you can definitely have die-offs that are just caused by the heat stress, and that can be direct, it just gets absolutely too hot for the plants. It passes a sort of a threshold where they aren't able to, basically they have to respire more and more as it gets hotter. And if their respiration rates go up too high, they can't photosynthesize enough to keep up, and they can just die. That way, you can also have those sort of high combination of heating events, and maybe low oxygen is also happening at the same time. And you can sort of have these knock-on events, but all of those things, you don't have to have disease to have a seagrass die off at all. But it may be this interactive stressor. And then, about the citizen science question. Yeah, so this is actually the sort of ultimate goal of developing ELIZA, the AI system. We would love to get it good enough that like folks could go out and just take a picture with your phone, and we could do some analysis to say, yeah, this looks like disease is present at this site or not. It's actually turned out to be a lot harder than it might appear to do that. And so we're sort of definitely several stages off from that, but it is possible to, it takes a little bit of time to figure out, okay, this is more likely disease, this is likely desiccation, but it's not that hard to sort of train your eye to identify those differences. And so, yeah, so I think in the future, we'd love to have a sort of citizen science component to this work. Yeah.
Great. And I guess, Lillian, are you familiar with the primed network at all?
Yes. Yeah. So I think, yeah, that would be primed is, so for anyone who doesn't know, primed is this network. I think folks at Oregon State are running it, and it's basically keeping an eye out for disease. So marine diseases. So, the sea star wasting disease kind of came as like a shock, kind of a surprise to everybody, that suddenly all of these really important organisms were dying, and people didn't have protocols in place, or people weren't ready to react. And so primed is sort of trying to build up our sort of readiness and our ability to say, hey, organism, we're seeing disease in this area, let's keep an eye out, let's coordinate sampling or protocols or other aspects. And so, yeah, I haven't been super active in primed lately, but I think there's a place for eelgrass disease there too. Yeah.
Yeah, I think it's through the iNaturalist program. If folks join the project, the idea is you can snap a photo of eelgrass and go, this looks healthy, this looks like maybe it's unhealthy, I'm not sure. And then you can have someone like Lillian or another expert go, hey, yes, that does, or like, no, that's actually something else, to kind of help gather some of that information to figure out where it is or might not be hitting. Just a reminder, if you have questions, feel free to put them in the Q&A or the chat box. I guess I should have maybe asked Jessi this as well, but in Washington State, there was the legislation that passed this past legislative session regarding eelgrass meadows and kelp forests, about restoring and conserving 10,000 acres, I think by 2040. My question is that enough? Do we need more? Are there additional things we should be thinking about? Or like, what would it maybe take to restore eelgrass beds? Because it seems like it's not just the physical aspect of, conserving and restoring the area, but there's some other factors to maybe consider that you kind of touched on throughout your presentation.
Yeah, that's a really good question. So I will say it's sort of a complicated and a straightforward issue, I guess. Eelgrass restoration, I would say, I think Washington is one of the leaders in terms of taking protections at the state level and really saying this is a priority habitat. We really care about eelgrass and kelp, although I don't really know as much about kelp, but yeah, I think that so those legislative kind of mandates almost are really good in that sense, that we have really strong protections. But it is a little bit complicated. I think that there's part of the challenge, like we don't always know. We see these losses of eelgrass and we don't always know what's causing them. And if you don't know what the cause is and you can't ameliorate that cause, then even if you restore plants, there's no guarantee that they're going to persist and that the restoration will be any more successful than the natural habitat was. Like if all the plants die and it's because of some, sedimentation, for example, which was brought up before, and we don't address that cause of sedimentation, all the effort to restore that area might be not really for a lot of success. And so I think there really is a challenge, especially with eelgrass, which is a little bit fragile. I don't know, it's kind of like a little bit sensitive. And so really trying to understand places that have a high likelihood of being successful if we do restore them is kind of is a priority. And I know that DNR has done a ton of work in terms of modeling habitat suitability, and I think that that's really important to sort of have a good foundation for this kind of work.
I guess maybe a follow-up question to that is, with sea level rise, there's been this, I guess, suggestion that as sea level rise comes up, eelgrass is going to want to, it can only grow so far out depending on how far the light can penetrate down because it's a photosynthesizer, but we have development. And so it gets sort of squeezed between not being able to move upshore too much. But in the drone photos that you showed, it looked like the eelgrass it was sort of receding back out towards the ocean. And so I was wondering if you had any thoughts on what might be causing that, or how that may or may not play a role in sea level rise. Is eelgrass maybe even more doomed than we thought if it's receding out to maybe deeper water? Maybe it's not as hot out there. I don't know. Any thoughts on that?
Yeah. So I think this is really key because you have to think about these kind of zones of habitability, right? And so like the seagrass, the eelgrass, it needs that light and it needs to not get too hot. And those are sort of the two things it has to balance. And it has to, can't go too far up in the intertidal because it'll get dried out, it'll get too hot, goes too deep, it doesn't have enough light. And so, yeah, with sea level rise, we definitely have, this kind of coastal squeeze where there's only so much, if you have development, that's a hard stop, and the ecosystems can't migrate inland against that development. And I think that with sea level rise, sorry, I just lost the thought that I was going to say. Oh gosh.
Okay.
No, I remembered it. Okay. So one of the things that the sort of eelgrass restoration community, and I think the kelp restoration community too, has started to focus on is, can we restore a little bit more in a little bit more targeted way than we might have? And so one of the things that folks are doing is looking for populations of donors that are really, for example, like heat adapted. Like if you find a population of eelgrass that's really resistant to heat stress, can you then use that as your donor population and put that in places where, okay, sea level rise, it's being pushed up the slope and maybe it's getting hotter, but it's actually okay with those conditions. For example, in Puget Sound, there's a population of eelgrass inside of the hook of Hood Canal that the water there gets really, really warm in the summer and the eelgrass is fine. And so maybe that's a population that we could use as a donor source and could potentially sustain some of these restorations in new places.
Great, thanks so much. I don't see any more questions, so thank you so much for your presentation. That was really great to end on. So much learned today, and I encourage everyone to maybe sit and think about and absorb all of the great stuff that we learned today on the latest and greatest science that's out there, how we can maybe better manage our shorelines to better protect our important resources that are out there. I think it's really great to see all the updates of using drones and artificial intelligence and models to help us better understand what's going on out there, and use community science too in the mix. I encourage you all to get involved by staying informed, urging decision makers to help protect these important shorelines, such as Cherry Point. And also just showing up, whether it's to a community science monitoring project, taking out your smartphone and participating in some iNaturalist project or something like that, or showing up to a Cherry Point Aquatic Reserve Citizen Stewardship Committee meeting, or a beach cleanup. There's many ways to get involved. Lyle, if you would want to add on ways to get involved or anything else, please do so.
I think Robert covered it pretty well. We have a meeting coming up next Wednesday, 3 p.m. It's a great chance to see, see how our meetings go and what we're concerned with. And I would just, really like to thank all the presenters. Just amazing information. And you too, Eleanor. Thank you for hosting this.
Yes, thank you, everyone, and well done. And I am continue to be blown away by all the scientist presentations today. I know I'm left with lots of great things to think about. And for next steps, we'll follow up by sending out a recording of this, as well as a few links on ways to get involved too, and some of the important links that might have come up in some of the presentations, so you guys can stay involved and informed. And thank you so much, and enjoy the rest of your Saturday. Maybe it's a little less rainy out there. So thanks so much. All right, take care. Bye, everyone.
Bye.